Okay, I guess that we can start. So it is a pleasure to start this morning session with Florence Merlevède. She is going to speak about quadratic transportation cost in the central limit theorem for dependent sequences. Please.
Thank you. So it's a real pleasure to be here, and I would like to thank the organizer for the invitation. So I shall speak about rates of convergence in the central limit theorem with respect to different distances. So this is based on joint works, because there are two works with Jérôme de Decker and Emmanuel Rio. So I shall start with a small introduction about what we have in mind. So let us start with a strictly stationary sequence of real valued random variables, and which is centered and with finite variance. So you take, you denote by Sn the partial sum associated with this sequence. So P Sn divided by square root of n will be the law of Sn divided by square root of n, and G sigma square will be a Gaussian centered with variance sigma square. And okay, we shall assume in all these work that in all this talk that the series sigma square, which is the series of the covariances, is convergent. And if I assume this fact, then as a consequence, we have that the variance of the partial sum divided by n is going, when n is going to infinity, to sigma square. Okay, so there are many different conditions answering the central limit theorem. And if you assume, for instance, that the variables are bounded, a very simple, and you are in the ergodic case, one of sufficient condition to have the central limit theorem, meaning that Sn divided by square root of n is going in low to a Gaussian, which is centered with variance sigma square, and the sigma square will be the series of the covariances, is that the summation of the norm 1 of the conditional expectation of xk, knowing F0 usually is just the sigma algebra generated by the xi for I less than 0, so the past sigma algebra. If you assume this condition, then you have the CLT, and this condition is known as the Gordon condition in L1. Okay, you do not have to assume that this is bounded, but if it is bounded, this is the only condition we need. Okay, so now you can ask yourself, can we have sufficient condition to get some sharp quantitative estimates of the approximation of the law of Sn divided by square root of n by the law of a Gaussian, having the which are centered with the second moment, which is the series of the covariances. And we are interested of this quantitative estimate in terms of the quadratic cost. So what do we mean by the quadratic cost? This is the distance in L2, the L2 minimal distance, which is defined as follows. So let us give the definition, the more global definition of LP, minimal distances. So you denote by L mu nu the set of the probability laws on R2 with marginals mu and nu. And for any P more than 1, you define WP between mu and nu. So why W? Because this is usually called the Wasserstein distances. And the Wasserstein distances between of order P between mu and nu is then defined as the infimum of all these quantities when P here is a probability law on R2 such that its first marginal is mu and the second one is nu. So if you just want to define this with so WP of mu nu is just the infimum of the expected value of x minus y at the power p. So let's say I'm going to put at the power p here, and x as low mu and y as low nu. Okay. So WP, either you say that it is the LP minimal distance or the Wasserstein distance of order P. And from results by Fréchet since 56, so you know that you have another way to write this Wasserstein distance of order P. You just take the generalized inverse. So F minus 1 is the generalized inverse of F, which is the cumulative distribution function associated with mu. And G is the cumulative distribution function associated with mu. And you take the generalized inverse. And WP between mu and nu, you can also write it like this. So when P is equal to 1, sorry, this is the inverse of the cumulative distribution function, but so it is the infimum. So F of F minus 1 of mu, I think it is the infimum over the X, which are in R, such that F of X is more than mu. Because it's not always neither continuous, neither strictly increasing. So it cannot be not bijective. And when P is 1, there is another way to define W1, and even two ways to define W1. Either you define, so W1 between mu and nu is also the integral between 0 and 1, the integral on R of F of t minus G of t dt. So this is special for P is equal to 1. And this is also the supremum over F, which are Lipschitz with coefficient 1 Lipschitz of expected value of F of X minus, so you can write it down like this, integral of F of d mu minus integral of F of d mu. So for W1, you have 4 writing to define the same thing. But when P is different from 1, okay, so this one is equal to this one, but there is no equality like this. Okay, so now the quadratic cost is just defined, it's just WP when P is equal to 2, and I take the square. So what I call the quadratic cost will be kappa 2 between mu and nu is just the Wasserstein distance at the order 2 square between the law of mu and the law of nu, and I will write it like this. Okay. So what are the previous results in the independent setting? So take now a sequence of RID, which are centered and variance equal to sigma square. And there is a first result by Bartfai in the 70s saying that if you have a exponential moment for the, so there is a Laplace transform for the xi, for some t strictly more than 0, then the quadratic cost between the law of Sn and the law of a Gaussian with variance n sigma square is capital O of n at the power epsilon for some epsilon strictly more than 0. And he conjectured in his paper that there is no epsilon. So just when you put the normalization square root of n, because these are distances, if I put a square root of n here, so here I have just sigma square, I have, because I have a square here, I have to divide by n. So if I put a normalization square root of n here, I will have capital O of n epsilon minus 1 to have the rate. So for Bartfai, he said, okay, in this situation, I do not have, it's just less than a constant. And starting from this result, he get a strong invariance principle. So Vivian talked about a strong invariance principle, and both in the almost sure sense and in the L2 sense. with some rate, and the rate you obtain is a little bit more than n at the power 1/4. So to be a little bit more precise, when I say that he got a strong invariance principle, he says that, okay, I can redefine my partial sum without changing its distribution on possibly a richer probability space on which you can construct a sequence Zi of AID centered Gaussian variables with the same variance, such that if I set BK, which is the partial sum associated to the Gaussian, then I'm going to approximate the initial partial sum by my Brownian motion with an error, which is a little o of Bn. So this is why I said a rate Bn, almost surely. So this is for a strong invariance principle in the almost sure sense. And if I want a strong invariance principle in the L2 sense, this means that I'm going to take the norm 2 of the maximum between of the difference between this partial sum, and it's going to be a little o of a capital O. I don't really care. Okay. So now concerning the BART5 result about the rate in for the quadratic cost. So there is a paper by Rio in 29 showing that if we have, so not only we can just delete this epsilon, indeed there is no epsilon here, but even you do not need to have a Laplace transform. It's enough for the variables to be in L4. So if you have a moment of order 4, then the quadratic cost between the law of Sn and the law of the Gaussian is capital O of 1. And it proves that this upper bound is optimal in the sense that if you denote by M for K, the class of probability laws on the real line, such that they have a first moment which is 0, the second moment, let's say it's 1, and the fourth moment, it's 4, it's kappa. And if you take a sequence of, you can construct a sequence of ID with a common law mu, which are in this class of probability laws, and such that the quadratic cost between the law of Sn we normalized and the Gaussian, which is variance 1, times n are more than constant here. So you cannot do better. Okay. So after this result by Rios, there were a lot of work on this, and especially there are some result by Bobkov, so more recent, saying that, so first Rio proved his result also not only for the quadratic cost, but for P between 1 and 2, saying that finally, if the random variables have moment of order P, then the rate for the Wasserstein distance at the power P, so here, between the law of Sn divided by square root of n and the law of a Gaussian, is of order, so it's not moment of order P, it's moment of order P plus 2. So they are of order 1, a constant divided by n at the power P over 2. So this result for P between 1 and 2 is in the paper by Rio. And for P strictly more than 2, it was proved by Bobkov with a completely different proof much more recently. Okay. And there are also extensions to INRD for this kind of result, which are given in Bonis very recently also. So both all these results are very specific for the independent case. Okay, either you use Stein method or you use a very precise expansion of the characteristic function. And you would like to extend these results to the case of non-independent random variables. So you would like to relax the independence assumption and find sufficient, and if you can have sharp conditions, that's perfect, condition in the dependent case, which is going to ensure that the quadratic cost between the law of Sn and the law of a Gaussian with variance n times sigma square, so this time sigma square is going to be the theory of the covariances, is a big O of 1. So when you are going to divide by square root of n, you will have this rate of convergence in the central limit theorem. And finally, we shall see, because when I talk about Barth-5 result, I said, okay, he was able, because he found some rate, let's say like this, he was able to prove strong invariance principle. It was much before the famous Kolmos major and Kuznetsov result, but with using this, he was able to prove something. So now, since we are in the dependent setting, we can say to ourselves, can we do a little bit like Barth-5 and prove a strong invariance principle if we are in the dependent case? Okay, in the dependent case, we shall see later, if we want to do as Barth-5, we need a little bit more than this kind of result. We need a conditional, so rate concerning the conditional quadratic cost. So you do not take the quadratic cost between the law of Sn and the law of a Gaussian. You are going to take the quadratic cost between the law of the partial sum knowing the past. So this is a conditional law, and the Gaussian. And after, obviously, this one is random, and you have to take the expectation. So having this, it's much, if you have this result, you can deduce this result. Okay, you have to write a little bit, but this one is a stronger result than this one. So if I have this one, I have this one. Okay, so what kind of condition? As usual, in the dependent case, you can ask yourself, what can I expect in the Markov chain setting? So, okay, I put Xn, irreducible, aperiodic, positively recurrent Markov chain with an atom denoted by A. Let's say that this is a Markov chain that we are studying when we are in master degree. So we have just a Markov chain on, let's say, N, or Z, whatever, which is irreducible, which is aperiodic and positively recurrent. So each of the points are going to be an atom. And in this situation, we know that we can do a regeneration scheme. So we can do ID cycle, even if each of the cycle, so there are cycles, and the number of the cycle is random. But whatever, you know that you can decompose your partial sum as a sum of ID random variables, even if the new sum is going to stop at a random time anyway. So for this Markov chain, I will denote by P the unique invariant distribution, and I shall say, okay, I'm going to consider the stationary Markov chain, meaning that the chain starts from the stationary distribution. And okay, let's just do, because we are in the bounded case, so I'm going to take xk, which is going to be a function of the Markov chain, and f will be a bounded function such that it is the xk are centered. So as I said, by the regeneration scheme, you can conjecture when f is bounded that each of the cycle, you know, is a random variable, which is like which behaves like the return time to the atom. So here, the return time of the atom I denote by TA, but in the usual case, each point is an atom. And So they are going to play the same roles as the initial random variables in the ID setting. So if I just make an heuristic, I said, okay, I have to replace expected value of x1 at the power 4 finite by expected value of so I take tau, the first return time to the atom, so expected value of tau at the power 4 when I start from the atom. Okay, so probably in the Markov chain setting, if I copy what did Rio, I have this result as soon as this one is finite. Okay, and now I have to understand what means this in terms of dependence condition. There is a result by Boltosen in the 80s when he proved Berry-Essen central limit theorem for Markov chains, saying that if you have this, it is equivalent of the fact that the summation of n square alpha n is finite. So what is alpha n here? Alpha n is what we call the strong mixing coefficient or the Rosenblatt mixing coefficient. And in the Markov chain setting, it can be rewritten exactly like this. So it's easy in the Markov chain setting to write this coefficient. So you take, so xn is f of zeta n. So you take expected value of your random variable, knowing the past, but in the Markov chain setting, the past is just one random variable, minus the expectation. You take the norm one, and you are going to take the supremum over all the functions which are bounded by one. This is the strong mixing coefficient. Sometimes you can change the class of function. If you take, for instance, the function which are only of bounded variation, this is what we call a weak alpha coefficient because it's a smaller class. So this is the alpha mixing coefficient in case of Markov chain. So what is our conjecture? It is that if you have this condition, so if you are not in the Markov chain setting, if you have this condition, then you will have this rate. This is what we would like to have. Okay, this condition when the random variables are bounded. So we are not going to use exactly this alpha coefficient because it's very easy to write when it is a Markov chain, but if it is not a Markov chain, it's not so nice. And there are many models where you can prove that the alpha n here is not going to 0. So think just about Bernoulli shift where the innovation are not does not have density with respect to the Lebesgue measure. So the alpha is not going to go to 0. So there are many models where this one is not going to 0, but there are some weaker coefficients that you can compute. So what coefficient we had in mind? This is this theta coefficient. Okay, it's just a series. It's just coefficient defined with the norm 1 and the conditional expectation. So for instance, what I will need, it's theta p is equal to 4 and q is equal to 4. Meaning that, for instance, I have to control the norm 1 of expected value of xk knowing the past minus the expectation. I have also to control norm 1 of expected value of xk plus u, let's say, knowing the past minus the expectation, up to I need to have I need to go up to a product of 4 here. Okay, but it's not so complicated. It looks bad, but it's not, because it's only here coefficients which are defining with conditional expectation of a product of random variable. So if you go back to the case of a nice Markov chain, So take zeta n irreducible aperiodic positively recurrent Markov chain with an atom, let's say. And you take a bounded function of this Markov chain, and you take the minus the expectation. Then if the return time to the atom has a moment of order 4 when I start from the atom, then this condition is satisfied. So summation of k squared theta k, which is finite. So finally, my objective, my goal is to prove that under this kind of condition, summation of k squared theta k finite, let us not think about the p and the q, just delay it in the future. So under this condition, then I have that the quadratic cost between the law of Sn and the law of the Gaussian is going to be capital O of 1. So this is what we did, and even more, as I told you, we also did the result for the conditional quadratic cost, and we gave the rate between. So remember, I said you if my objective is to prove that summation of k squared theta k finite will imply that I have that this one is the capital O of 1. Okay, I consider first my condition is summation of k theta k, which is finite, and now I have all the rate between if I impose this condition and if I impose this condition. So this is why here I have a bound which depends on the rate I will assume for my coefficient. So indeed, if you assume this condition, then you will have that this conditional quadratic cost will be bounded by a constant. So this proves the heuristic we had in the Markov chain setting. And also in the Markov chain setting, just a simple remark. If you have this kind of result for the conditional quadratic cost, it means that if you use only, let's say, Schwarz inequality, you can have a bound for the expectation starting from a low mu, and mu, as soon as mu has the density with respect to the stationary measure, and the density has to satisfy this condition. So you can have some result in the Markov chain setting, even if you do not start from the stationary distribution. Okay. So if you have strong mixing sequences in the sense of Rosenblatt, and if you are not, especially in the Markov chain setting, okay, since your coefficient alpha are going to bound your coefficient tau, it means that your result applies to the case of bounded functionals of strong mixing sequences in the sense of Rosenblatt. So if you have a result about the rate in the quadratic cost, you have a result in terms of Berry-Essen theorem. So distance in the sense that I'm going to look at the uniform distance. So meaning that, okay, I'm going to define the Kolmogorov distance between the law of Sn divided by, here I took the square root of the variance. But the square root of the variance is going to behave like square root of n. So I define delta n, which is going to be the Kolmogorov distance between the law of Sn divided by square root of n, by sigma n, and the standard distribution, normal distribution. And if I know that the summation of the k squared theta k is finite, then the quadratic cost is going to be of order 1 over n, because here I have divided, I have taken the normalization, so 1 over n. And we know that the Berry-Essen, this distance is less than the quadratic cost at the power 1 over 3. It's just due to some relation with distances between the Kifan distances and these Kolmogorov distance. And after, when you want to bound the Kifan distances with the help of the conditional, with the help of the quadratic cost, you just use Markov inequality. So you have this relation. So it means, sorry, I'm too fast. So it means that under this assumption on the theta coefficient, you have a Berry-Essen bound. Okay, it's not the very good one. You would like to have better, but at least you have something. And in the dependent setting, it's not easy to get a Berry-Essen bound. But Berry-Essen, okay, we think a little bit, and okay, it's good to have a rate of convergence in the central limit theorem. And we wanted to apply Berry-Essen to say, okay, if I want to give some estimate of the quantile function, so I take the generalized inverse of the cumulative distribution of the law of Sn divided by the square root of the variance. And I would like to know if it is very close to the quantile of standard Gaussian. And if you use, you have this relation, delta n is the Kolmogorov distance. So it means that this is of interest only if you, where you are looking at the quantile, is not too close to 1 and not too close also to 0. So on a bound, your Berry-Essen theorem is not going to give you anything for to have a good estimate of this by this. But if you take the bound for the quadratic cost, you can prove the following. So the same, except that you are allowed to be close to 0 and close to 1, not too close. You have to have epsilon n, which is going to go to 0, and n epsilon n is going to infinity. But it's a little bit more precise for the estimation of the quantile. Okay. So I would like to give some application to dynamical system and their associated Markov chains. And I shall only talk about the following toy model. So this is what we call the Liverani, Sossol, and Vaianti map. It is an intermittent map. So between 0 and 1 over 2, this is the graph of the map with parameter gamma. So gamma is between 0 and 1 here. And here, it's 2x minus 1. So there is a fixed neutral point, which is 0. It's non-uniformly expanding, and you are going to iterate this map. What do you know about this map? Very, very quickly. Okay, there is only one absolutely continuous invariant probability measure nu, and it's density. So either I put I index by gamma. Sometimes I do not index by gamma if it is not necessary. And so the density of nu is bounded below and above by a constant divided by x at the power gamma. Okay, in this situation also, you can associate it to this to the iteration of the map a Markov chain that I call zeta. So the invariant measure will be nu, and what it is important, it is that the iterate of t, so t squared, tn, is distributed as the Markov chain, but in the reverse time. They do not live on the same probability space, but at least they are distributed, but they have the same distribution. So what is the transition operator of the Markov chain? It's only the Perron-Frobenius operator defined as follows. So the Perron-Frobenius operator I will define by K here. Okay, here it's just a line to verify that indeed K is a transition kernel. This is due to the invariance of nu, plus obviously the definition of the Perron-Frobenius operator. And due to the fact that T squared Tn is distributed as the Markov chain in the reverse sense, you know that if you want to study the quadratic cost in the CLT of the partial sum associated to some functional of the iterate of your map, so here you are on 0, 1 with the measure nu. This is equivalent to study the same question, but for the functional of the Markov chain. So studying this one or this one, the quadratic cost for this one or for this one, it is the same. But we are not in a situation where we can use a regeneration scheme like for usual Markov chain. And we know also that this Markov chain is not strong mixing. But this Markov chain, you can compute the theta k coefficient in different situations. So when the functional are of bounded variation, so BV, this is the space of bounded variation function. So the norm of the bounded variation function will be denoted by a double bar, and it's going to be equal to the infinite norm of f plus the variation norm. And for this norm, what can you prove? You can prove that when you look at, so it's like looking at the norm 1 of the expectation of f zeta n, knowing z0 minus the expectation. So it's like looking at a theta k, theta n, sorry. And so this theta n is, or even the weak alpha, let's say, is less than a constant times the norm of f divided, what it is important, by n at a certain power, and the power is 1 over gamma minus 1. Yes. Here? It is because you integrate. You take the norm 1. Okay. And also you can prove what it is important also. It's not only this one, because for this, it means that you can compute only one. So it's like you compute the norm 1 of expected value of f of Cn, knowing C0, minus the expectation, norm 1. But if you want to compute two of them, so f of Cn and f of, so Cn, f of Cm, minus the expectation, so you subtract only the expectation, you have two of them. So you need to have for the, you need to prove that for the transition kernel, use the transition kernel here, so there is a kind of stability, you know, so you keep, it's a kind of invariance here. As soon as you compose f by k, you are still of bounded variation, and you can bound by a constant times the norm, the bounded variation norm of f. So it's a kind of invariance here. So both of them are important. This one only to prove for one. So if I have only f of Cn, but if I have two or even more, I need to have this bound. So as a consequence of this affair, so this is something that we prove with Sébastien Guézel. And so as a consequence, if f is a function of bounded variation on 0, 1, and you take a function, so xi, a function of the Markov chain associated with the LSV map, then the theta coefficient will behave as follows. So as soon as gamma, the parameter of the LSV map, is strictly less than 1/4, and f is of bounded variation, the quadratic cost between the law of Sn and the law of the Gaussian is bounded by 1. Okay, and this bound also holds if f is Hölder continuous. You can prove also that the theta for Hölder continuous function, not with the same arguments I gave before, but in case of Hölder continuous, you can prove also that the bound, this bound is satisfied. So you have also this one. So a few words about the proof. So it is based on the Lindeberg method. Why the Lindeberg method? It is that it can be extended to the dependent case. It's not the case for Stein method or method on characteristic function. It's more complicated, but for the Lindeberg method, it's very nice. But even if it's nice, it's techniques. So I shall assume a very simplified framework. And my simplified framework will be, okay, I take a sequence of martingale differences. Okay, so fk minus 1 is the sigma algebra generated by the xi I less than k minus 1, such that the conditional variance is constant. The moment of order, the conditional moment of order 3 are also constant. Okay, I do not take 0, but they are constant, and they are in L4. So, okay, it's very simplified, but even in this context, how to do? So there are two facts. The first one, I need it because beta 3 is not equal to 0. So what I'm going to do, because if I take a Gaussian, here, a Gaussian, its moment of order 3 is 0. So if I take only a Gaussian, it's going to share the same 2 first moment, not the same 3 first moment, and I shall see that I need the 3 first moment, which are going to be the same. So I take a Gaussian, I take an independent random variable b, which is, so it's enough, it has only 2 values, let's say m and m prime, and b will be such that it is centered. The moment of order 2, sorry, it's not sigma square, it's sigma square divided by 2. There is a mistake here. And the moment of order 3, it's beta 3. I take this, I call it y. So these random variables, they are very good because they have Laplace transform. Since they have Laplace transform, if I take the quadratic cost between the convolution n times of the law of the y and a Gaussian, I can prove, and it is in the Rios paper, this is the first tape, it's a capital O of 1. It's not so easy because it's based on some lemma which are in Kolmos, Major, and Tusnadi paper, but okay, this is a fact that if you have random variable with Laplace transform, it's not so complicated to prove this one. So you have to prove that the law of the partial sum, the quadratic cost between the law of the partial sum and the convolution of the law of y is a capital O of 1. And to do that, you shall use Lindeberg method. To use Lindeberg method, first, you need to recall a fact. It is that the Wasserstein distance at the order 2 between the law of mu and nu can be compared to what we call the Zolotarev distance of order 2 between the law of mu and nu. Meaning that when I recall you the Wasserstein distance or Kantorowicz distance of order 1, I told you, okay, W1, I can write it down like this. And here, this is Lipschitz with coefficient 1, with parameter 1. Okay, when I take a 2 here, I do not have equality. I have an inequality, and the class of function is not going to be Lipschitz, but it's C2, and the second derivative is bounded by 1. There is a kind of comparison. And because of this comparison, now you have to look at rather kappa 2, Zolotarev distance. Or sometimes they are calling that ideal distances. Okay, we shall see why a little bit of ideal. Lindeberg method, it's based on 3 stuff: smoothing, replacing, and the Taylor expansion. So you take a sequence of ID with law pi, independent, so pi is the same law as y, independent of the initial random variable. Z is a Gaussian. So you add a Gaussian to smooth a little bit. And you want, so T and K, it's the sum, but with respect to the y, and they are going in the other side. I start from K, and I'm going to up to N. And I have to control this one, expected value of f, the partial sum of the xi plus my Gaussian, the partial sum associated with the y plus my Gaussian. First, you do a telescopic sum. The only difference is here I have a yk, here I have xk, here I have a yk. And here you see it's a nice function. It's a Gaussian with a convolution with this one, and in this one I have also some Gaussian. So it's a random variable having a density which is very smooth. So even if f can be only derivative, it has only 2 derivatives anyway, you have another function here by convolution, making the fact that f is in C infinite. So you can derive many times. So you have, I replace f by this one by convolution, you see, and this function is very smooth. And not only very smooth, but when I compute the derivative, I know that they behave like this. So for instance, the fourth derivative is 1 divided by n minus k plus 1. Okay, just another. So I do Taylor expansion at some point. I have the first 3 terms. They are 0. Why? Because I was, okay, I have to take conditional expectation. But anyway, the moment of y are equal to the moment of x up to the order 3. So they are destroying. I have just a rest. For the rest, you have the fourth derivative. If you do not think too much, so the first derivative is of order 1 divided by n minus k plus 1. I take the summation, I have a logarithm. Okay, so if I do not do too much, I have a logarithm of n. Either you can be satisfied with the logarithm of n, either not. If you are satisfied, okay, good. If not, you need much more works. But okay, and even in the independent case, you need much more works. But anyway, but imagine if you did not take a random variable having the same 3 first moment, only the 2 first moments, I will lose much more because the term of order 3 is not 0. And when I make a summation of 1 divided by square root of n minus k, I will have a square root of n. So if I didn't have moment of order 3 which are equal to this one, here I will have a capital O of square root of n. So, okay. Just another application about rates in the ASIP. In fact, if I have this, this kind of result about the expectation of the quadratic cost, conditional quadratic cost. If I copy the BART5 result, so we construct exactly with the help of conditional, I will not have time, but the conditional quantile transform, I can really construct the Gaussian random variable which are implied in my almost sure invariance principle. So I construct them. It's not just like this. And I can, because of this, in my construction, I can control the error I'm doing by replacing my blocks of random variables by some Gaussian. I need also a new deviation inequality anyway, but for instance, when I look at the Liverani Sossol-Vaianti map, and when I take observable which are of bounded variation, if they are older observable, I know already the rate in the AZIP. It's n at the power, let's say, gamma, plus a logarithm. We prove it with Christophe Cuny, Jérôme de Decker, and Alexei Korepanov. So when f is older continuous, okay, we have all the rate we want. But when f is of bounded variation, our method of proof with my co-authors doesn't work. So we need another proof. And so for instance, what we were able to prove, I try to be very precise, not to say I'm going to enlarge my probability space. So I enlarge it, but I say I can say how. It means that I have to take a product here, because I need to add another uniform distributed random variables, which is independent of the other random variables. So on this probability space, when I take gamma between 0 and 1/2, okay, I'm able, so the I here is going to depend both of y, of I, of x, and of y. And so they are Gaussian, they have variance, they are ID, variance sigma square, and the rate is the following. So let us not too much discuss about the additional logarithm term. What you have to look is the following. So when gamma is between 1/4 and 1/2, we have the best rate we can. Okay, but we are limited to gamma. If gamma is less than 1/4, we cannot do better than 1/4 because of our method of proof. But at least we have bounded observable which are of bounded variation. Okay, and I think I'm going to stop here. Thanks.
Thank you. Do we have questions? Okay, I have some question, just one. So this strong mixing condition that you have for theta in the dynamical systems world, let's say it's enough to have some system that has exponential decay of correlations. In that case, you have it like sort of automatically, this assumption on the convergence of the series, or because in the case of LSV, you had this polynomial decay.
Okay.
So you could bound like 1/n to the 1 minus 1/gamma. Okay. In the case you have exponential decay of correlation, you can say more there is a relation, or it's something unrelated.
No, I think it's not going to give you more information.
Okay.
What I can say it is that for dynamical system, which are a large class of non-uniformly expanding maps, as soon as you can model them by Young tower, and if the moment of the return to the base of the Young tower are of a certain order, you will deduce a rate of decay of the theta coefficient.
I see.
But for this method, even if you have faster decay of your coefficient, you are not going to do better than n at the power 1/4. It's not for the same reason than the Skorod and bending theorem, but it's for another reason, meaning that this method, if you are able to compute expected value of WP at the power P, is not going to help you more. So for this method, it's limited to 1/4.
Okay, thanks. Let's thank the speaker again. Okay, welcome back. And our next speaker is Frédéric Faure, and he's going to speak about a relationship between quantum dynamics and classical.
Yes.
Okay.
Thank you very much. Thank you for the invitation, and I'm very happy to be there. So yes, this talk is to speak about relation between classical and quantum dynamics. It's a point of view of geometry and dynamical systems. And at the end, so it will be a way to speak about recent collaboration and work with Masato Tsuji. So I start with an introduction. And I would like to present the talk with a kind of picture. So in physics, there are different theories that concern waves. For example, in electromagnetism, you have a wave equation. In quantum mechanics, you have a Schrödinger equation. And they concern the evolution of waves, linear PDEs. And it is known, it's called the semi-classical limit, that in the limit when the wavelength is very small, or equivalently the limit of high frequencies. So the frequency, I will call it omega, but it corresponds somehow to the inverse of the h bar, the Planck constant in quantum mechanics. When it goes to infinity, then the evolution of waves somehow can be described using Hamiltonian dynamics. Modeled by a vector field. So maybe I say Hamiltonian vector field X on the cotangent bundle of the manifold where the wave is a function. And somehow it means that if for the wave you consider a small wave called wave packet, then this wave packet for a short time will follow the projection of the Hamiltonian flow on the manifold N. But, for example, for the wave equation, there is a Laplacian operator that is a second order differential operator. But if you perturb this Laplacian by a first order operator, then in the limit of high frequency, this perturbation will not affect the limit. So different operators, infinite number, may have the same limit. So it means that this is not a unique correspondence. You may have different equations with different operators. So different spectra. That may have the same classical limit. So it shows that it is known, for example, that from the spectrum, you can determine, for example, in some case, the set of periodic orbits, but not the converse, of course, because it's not unique. Then, so this, as you know, Hamiltonian vector is a very geometric, it's a symplectic geometry. And in the 70s, some people, Constant and Suryo and other people, wanted to put this framework in a geometrical framework. And so it's called the geometric quantization, a way to recover the Schrödinger equation from the Hamiltonian dynamics. And from this, I will explain, there is a unique correspondence between this dynamics and another dynamics that in dynamical system theory, we can call a contact R extension. And in physics, it is called the pre-quantum dynamics. And it's a vector field. This vector field lives on an additional, a bigger space with one-dimensional more, I will explain. And it's, say, up to global choice, it's a unique, so it's equivalent problem. And okay, I will explain very detail. Okay. Then you will see that in this dynamics, you see very nice aspects of quantum dynamics already. But this dynamics takes place on the cotangent bundle times additional space, which is a neutral direction, and not on n. Okay, so it's not exactly quantum dynamics. And so to recover quantum dynamics, these people restrict this dynamics to functions that are constant on the fibers. Okay, it's like a ad hoc choice. So they restrict to this, and they obtain somehow the Schrödinger equation or wave equation. They can restrict to fibers which are Lagrangian foliation or to any Lagrangian foliation. The problem is that so you have many choices, infinite number of choices, so you obtain different results. It is called geometric quantization, where you restrict the push forward of that dynamics along Lagrangian fibers. The problem is that usually the fibers are not invariant by the dynamics. Okay, so it is not very natural to do this. And it is called geometric quantization. And sorry, sorry, it's R. Okay, R, just R. I call R underscore Z to say that Z will be a variable I will use. Okay, it's R. Okay, but I will explain. This is just an introduction. And in fact, with Masato Tsuji, we considered a very special case of dynamics, which is Anosov geodesic flow. And for that dynamics, as you know, there is a natural Lagrangian foliation, which is invariant by the dynamics, which is, for example, the stable direction or the unstable direction. So a good idea is to consider this geometric quantization using stable or unstable foliation. Okay. And in fact, even more, you don't need to do this because, as you know, if you consider the push-forward dynamics, okay, it will expand functions along the unstable direction. So by under time, for long time, functions naturally will become constant along the unstable foliation. Okay, so it's like the dynamics itself, by the process of time evolution, will project to functions that are constant along the unstable foliation. Okay, and somehow it's the result I would like to present is that if you consider, so this is very special for Anosov geodesic flow, which is Hamiltonian dynamics, then just you wait, you consider long time evolution of this, okay? Just wait, and then after some time, not very long in fact, because it's converge exponentially fast, you obtain some quantization. So in this infinite list, there is some quantization that you obtain. We can call this maybe a dynamical quantization. And it corresponds in this language to restrict to functions that are constant along the unstable direction, more precisely distributions. And so it has the same principal symbol as all the quantization, okay? The same, but the correction is special. Somehow, from the spectrum of this operator, you can obtain exactly the periodic orbits. It's using, for example, trace formula or zeta functions. And for example, in the case, I will explain this. In the case of geodesic flow on constant curvature manifold, where you can use group theory, there are many works, for example, Flamminio-Forni, then you obtain exactly the Laplacian. But in general, not. Okay. Okay, so this is the introduction. I will start to recall the formalism of this. Then I will explain what is a contact air extension. Then I will very quickly explain how people did geometric quantization, how you obtain the usual operators in quantum mechanics, maybe you know already. And I will finish to explain this result. And this is not the final result. I guess there are many interesting things to explore in this work. So, the first object I would like to write is you consider a manifold, and I will use the notation Q as a point on this manifold. In physics, it corresponds to position of a particle, and P for a cotangent vector. In physics, it is called the momentum. And as you know, on the cotangent bundle, there is a natural one form, which is called the Liouville one form. I will call it A. In coordinates, it's just you take the components of the cotangent vector times the derivative of the coordinates on the manifold. And you observe that the derivative of this one form, so these two forms, maybe we use conventionally a minus, is a symplectic two forms. Okay, it's canonical. In fact, it does not depend on coordinates. It's canonical. And then from this, this two form is non-degenerate. So if you take a function on the cotangent bundle, it defines a vector field X by this formula, and in coordinates, this is this formula. Okay, this is called the Hamiltonian vector field. And it generates a flow on the cotangent bundle. Now I would like to explain this air extension that is called also the pre-quantum dynamics. So for this, so it's called pre-quantum dynamics, after the work of Suryo and Constant in the 70s. So for this, you consider an extended space, which is the cotangent bundle, and you add a one-dimensional direction, and I will call Z the variable. And on this extended space, you consider one form. Naturally, it's a contact one form. It's dz minus A. And you observe that the derivative of this one form, ddz is 0, so it's minus dA, it's omega. And if you want, the picture of this setting is that you have on the base the manifold with position and momentum. This is the cotangent bundle. On this space, you have a vector field, and if you integrate, you have a flow. And we have added a direction. Okay. And on this extended space, P, we have this one form, and we can represent this one form by its kernel, if you want. This is hyperplane, the kernel of theta. Okay. And you have a distribution which is non-integrable. And so what people do is to lift this vector field and that flow on this space. And there are a natural way to do this. So we define the lift vector field, called also the pre-quantum dynamics, to be the horizontal component is X, and there is a vertical component, so a component along the Z-axis. And this function is supposed to not depend on Z, so it's called equivariant lift. It's invariant by vertical translation. It's a function, L is a function of the base called in physics Lagrangian. So the function L is the one form contract, the Liouville one form contract with the vector field X minus the Hamiltonian function. So if you want, in coordinates, A is P dq, so it gives you P, G, and the horizontal component of X is the velocity, minus H. Okay, so this is the well-known Lagrangian function in physics. Okay, so what it means is that we have here a lift dynamics, okay? And no, so I will explain what is. No, sorry. It's not horizontal lift. It's not vertical, okay? It's not the rip flow, neither. It's not the horizontal lift. It's another natural extension. And this extension is set such that it preserves theta. It preserves theta. So I claim that the Lie derivative of theta with respect to x tilde is 0. It means that, okay, it will preserve this distribution of kernels. And exactly, I will, yes. I first prove this and after I comment. Okay, maybe you can record this picture. I will erase. So we are here. Okay, just the proof is very simple. So the Lie derivative of theta from the Cartan formula is the contraction of theta with x tilde d minus contraction theta d. Okay, so here, when you contract theta with x tilde, you see you have L minus AX. And the contraction of x tilde with d theta is the contraction of x tilde with omega. So it's a contraction of x with omega. And the contraction of x with omega is dh from Hamiltonian dynamics. So minus dh. Okay. So you see from this construction that Lagrangian minus a, maybe, sorry, there is a minus. Okay, so L minus ax plus h is 0. Okay, this is so this is called the natural extension that preserves this one form theta. And I would like to give two important examples. So, for example, you consider a manifold with a Riemannian metric, so a Riemannian manifold. And in mechanics, people consider the Hamiltonian function, that is the norm square of a vector, cotangent vector, divided by 2 some constant, which is the mass. It is called kinetic energy, plus some function on the manifold. It's called potential energy. Then the Lagrangian is, when you take this formula, you get the kinetic energy again, minus potential energy. Another important example that we will use after is the geodesic flow. So for the geodesic flow, you consider again a Riemannian manifold, but now for Hamiltonian function, you take just the norm of the cotangent vector with respect to the metric. Then you compute that the Lagrangian is A contracted with X, in fact, gives again a norm of P minus Hamiltonian. So you get that the Lagrangian is 0. So it's equivalent on the energy shell, okay, but not globally. Maybe this is more natural. Maybe not, but we will see it is more natural from this point of view. Yes, you can, in fact, you can take any power of P. So maybe I consider this, okay? So with this, for this dynamics, you see the vertical component of the lift vector field is 0. So in fact, x tilde is the same as x, okay? We don't need this extension. So after, we will forget this extension, but we have to keep in mind that nevertheless, we work with that pre-quantum dynamics. And no. Yes. Yes, it's yes, it's equivalent. No, I will like to insist there is no freedom. You start from Hamiltonian dynamics, and this setting is somehow unique, okay? Because Okay, theta is defined from. Yes. Ah, okay. Yes, so you are free to consider the. Yes, exactly. You from a given choice of function h, we have. Okay. Yes, of course. And this is just examples. Okay. Now, as you know, when the dynamics is chaotic, instead of considering trajectory of particles, it's better to consider the push forward of densities. Okay, because from this you will have good description of statistical properties of the dynamics. So now we consider the push forward as it is usually done in dynamical systems, push forward of functions on P, on this extended space. Okay, but because the dynamics is somehow trivial along the z direction, because it is equivariant, instead of considering any functions, we can do a Fourier decomposition along the z direction, and it will be preserved by push forward. Okay, so it's natural to restrict to a reduced space. So we called omega the frequency along the z direction, and in physics, it's usual to call it 1 over h bar. And so we consider the reduced space as the space of function that depend on the base, okay, qp if you want, or p, and z. But along z, this is a Fourier mode with a fixed frequency omega, and it's any function on the horizontal cotangent bundle. So V is any function on cotangent bundle. Okay, so this space somehow is equivalent to a space of functions on the cotangent bundle, but with a prescribed frequency. Ah, yes. The notation, okay. P, as I said at the beginning, is a point on the cotangent bundle, and Q is a projection on N. Okay. And as you did a remark that if you consider on the base, for example, a periodic orbit, okay, this is a remark, okay, just to have this in mind. You take point P and you take the flow, and this is a periodic orbit. Okay, it means, so if it is a periodic orbit for the dynamics on the base, maybe it's not a periodic orbit for the lift dynamics. Okay, just say that you come back to the same fiber. And the change is the integral of the Lagrangian along this trajectory. Okay, but if you restrict to this space are just oscillating in the vertical direction, you will have a change of phase here. Okay, and this change of phase is just exponential of minus e omega. Okay, and the shift. So the shift is integral of Lagrangian along the trajectory, and omega is 1 over h. So you have this. Okay, and it's a well-known, which is called the action in quantum mechanics. Okay, and so you see that the actions, so interferences effects, come from this, will come from this. And some mechanism like the uncertainty principle will come from this. So this is a remark. And people in the 70s were very happy to observe this because it's a sign that we are in the good direction somehow to obtain quantum dynamics. So what they did, we said we consider okay the push forward of functions. So you take a function at time t in this space. Okay, and you push forward, it means that the generator is minus the vector field. Okay, this is just the transport, natural transport. And okay, maybe I do something which is a void. I just multiply by I h bar. And you obtain what is called the pre-quantum Schrödinger equation. So people call this the pre-quantum operator, pre-quantum h bar, from the Hamiltonian function h that you have chosen. It's called the pre-quantum Schrödinger equation. And now I would like to comment on it to compare with the true Schrödinger equation in quantum mechanics. Yes. It's first order. Sorry, it's not exactly first order because x tilde, okay, it's equal to so minus e h bar x, okay, this is a vector field, minus L. So it's zero order correction. Sorry, t is a parameter which is time. Okay, you have a family of functions, and you suppose there are solution of this equation, which is just the push forward. Okay, and just I write like this. Okay. Okay. Some property is that for any functions, so some Hamiltonian, okay, arbitrary, then if you consider the commutator of these two operators, it's obtained from the commutator of the vector field, and as you know, it's related to the Poisson bracket. But we have multiplied by E h bar, so it gives this. Okay, this is what okay you have in quantum mechanics, but also in classical mechanics. But what is nice here is due to this zero order correction, if you take the function 1 for the Hamiltonian, then the vector field is 0. But here you will have 1 again. So you obtain the identity operator. So formally, it's the same algebra of operators as in quantum mechanics. But the problem, of course, is that we don't work on the same space. Here we work on the functions on the cotangent bundle. In quantum mechanics, this is function on the base. So to pursue this construction, people did what is called quantization, or geometric quantization. So they restrict that dynamics to functions that are so from L2 on the cotangent bundle to L2 on the base. So two functions that are constant in the fibers. As I said, this space function constant in the fibers will be not invariant by that dynamics, of course. Okay, so they define the generator op of h bar, so it's called the quantization. They take this operator and maybe it's not very rigorous. They restrict using a projector, okay, a restriction on functions that are constant. So it means infinitesimally you evolve function, but you average on the fibers. Okay, so it's a different problem, of course, and they write the Schrödinger equation with this operator instead of this. Okay, so I would like to say that it's a different problem. Yes, this, okay, for me, this P is a average, is a projector, okay, restriction to function constant. But of course, it's here the fibers are not compact, okay, so there are difficulties, but it's a, I will not continue after with this, okay, so I just, but in some settings, the fibers are compact, so it's average. But what is nice is that by construction, you have a dynamics on function on the base, okay? And if you look at what operators, what algebra you have, for example, if you quantize the position operator, so the Hamiltonian is QG, then this is the restriction of the pre-quantum operator obtained by Hamiltonian QG, which is the vector field X plus QG. But because we restrict to functions constant in the fibers, this operator has no effect. So what remains is QG. So multiplication by QG, as usual in quantum mechanics. And similarly, if you take as Hamiltonian the components of a cotangent vector, similarly, you obtain minus EH bar d over dQG. So this is the usual Weil-Heisenberg algebra of quantum mechanics. Okay? And the commutator gives a EH bar identity. So we recover quantum mechanics like this. But the problem, as I said, is that this operator restriction does not commute with the dynamics. Okay? In fact, here I said that you can consider the fibers, but you can consider any Lagrangian foliation to do this construction, and it gives you very interesting geometric quantization settings. For example, people like to consider a Lagrangian distribution that is complex. It's called Keller quantization. And in 79, Victor Guillemin wrote a paper where he suggests to consider the Lagrangian foliation for Anosov dynamics, the Lagrangian foliation defined by the unstable or stable direction. It was a suggestion because technically it's difficult because it's non-smooth foliation and the leaves are non-compact and dense. Okay, so it's not easy. You can play this game. Okay, you will not obtain exactly the Laplacian, but an operator which is equivalent in the limit of high frequencies. Yes, yes. Yes, yes, yes. So I did this just before coming, and you can play with this, but somehow it gives you some quantum mechanics which is equivalent in the high frequency limit with the usual one. But in physics, you have to maybe, I think in physics, physicists don't quantize classical dynamics of Newton. They just observe experiments and they find a good operator that match with the experiments. Yes, but exactly. But in accordance with experiments. So it's not their own choice. Sorry? Just had a process associating in a canonical way the quantum operator to an classical operator. Wouldn't say that finally quantum mechanics is not Yes? Maybe not. Okay. Maybe I would like now to discuss this kind of questions. Okay. So I have to hurry. So I go to the final point. We consider a special case, which is Anosov, geodesic vector field X on a manifold, which is the cotangent bundle, but restrict to the energy shell 1. Okay. So remember that the pre-quantum dynamics is equivalent to the Hamiltonian dynamics. Okay. And so I would like to give in this setting 2 results. The first one from Butterley and Liverani. And after there have been some different expression of this result by people using a different space. But for what is important here is the following. So for any constant, positive constant, there exists some Sobolev space. So Sobolev space means it's a space that contains smooth functions on this, I suppose, compact. It contains smooth functions, and it is defined using a function, a weight function on the cotangent bundle. Okay, like usually we define Sobolev space. And in this Sobolev space, the vector field is a generator of a group of operators. It has discrete spectrum called Ruelle discrete spectrum that is intrinsic mean it does not depend on the space that you choose. And this discrete spectrum is on the right of minus C, the constant. So it means that you have this picture. This is the spectral domain. And you take arbitrary large C, so minus C is very far on the left. And in fact, you have some essential spectrum in a vertical band here. But this vertical band, you can push it on the left, and it reveals some discrete spectrum that is intrinsic to the dynamics, called Ruelle spectrum. For this spectrum, what is obvious is eigenvalue 0, because it's constant function. The other one are not obvious at all. But with Masato Tsuji, we showed that for Anosov geodesic vector field, this discrete spectrum is contained. So this is a work with Masato Tsuji. The spectrum, this discrete spectrum, is contained in some vertical bands that I call B0 epsilon. So for any epsilon, B1 epsilon, etc., and some horizontal band, H epsilon. So H epsilon is some domain like here. Okay, it means here you may have some discrete spectrum, but we don't know about it. And there are some vertical bands, B0 epsilon, B1 epsilon here, but no spectrum here. Okay, so here it's empty. It's called a spectral gap. You have spectral gaps between these bands if the bands are separated. And so for the bands are, so they are vertical bands. Okay, maybe I draw like this, and horizontal band. So, and the estimates on these bands are given by the following. It's gamma k minus for band k. K is an integer. So this is the index of the bands, 0, 1, 2. So the left part is called gamma 0 minus, the right part gamma 0 plus, and it is given by the action of the flow itself, x, not on functions, but on a natural vector bundle. This vector bundle, I call it fk. It depends on the band. I will define what it is. And you consider this operator, which is just a transfer operator, okay, acting on sections of the vector bundle. And you consider it in L2 norm, it's bounded operator. You take power 1 over t, the logarithm, and the limit of long time going to plus or minus infinity. And it gives the estimate for the right side or the left side. They may overlap. Yes, they may overlap. Except, for example, if you are close to a constant curvature case where there are vertical lines. So this vector bundle is the following, is polynomial k along the stable direction. So polynomial k means homogeneous polynomials of degree k on the stable direction. This is the stable direction of the dynamics. This is a vector space. Okay, and this is polynomials of degree k, but you have to correct by a line bundle, the determinant line bundle along the stable direction, power minus 1/2. It's called the half density. Maybe a comment, just this is the stable direction because here we consider the vector field x. So it corresponds to the pullback dynamics. Okay, and in pullback, functions expand along the stable direction. So what you expect from what I said, for a long time, functions become constant along the stable direction. Okay, so constant along the stable directions, it corresponds to polynomials of degree 0, because polynomials of degree 0 corresponds to constant. Okay, and indeed, this result says that here, distributions that corresponds to this spectrum somehow corresponds to functions that behaves like a constant in the stable direction. And tensor product? Okay, this is first a line bundle. Okay, so determinant is just the space of forms. Okay, this is a rank 1 vector bundle. Okay, modulus means densities. Okay, for any space with a measure, for any space you can consider this bundle. It's a line bundle, so it will correct. This is a vector bundle, and this is a line bundle. In fact, we consider this, it comes from the analysis, okay, maybe it's not a choice to put it. It comes from analysis, it explains this gap here. No, sorry. Huh. Okay, maybe I just wanted to say that the theorem says that the discrete spectrum is concentrated. Sorry, it's alarm. The discrete spectrum is concentrated on some vertical bands set, and the estimate on these bands is given by another problem, maybe. Okay, it's just the vector field, where instead of pullback functions, you pull back sections of a very special vector bundle, okay? But you have to imagine this is a vector bundle over M, which is the cotangent bundle, okay? I claim this is a very natural vector bundle to consider. Okay, and I can explain why it's very natural. It's in fact in the proof of this theorem. But because space is time is finished, okay, I would just like, this is not a concluding work, it's just a sign, okay, and that for long time dynamics, okay, because this structure has real part very negative, it will dump very fast with positive time. It will disappear. And for long time, what is important is the spectrum near the imaginary axis. Okay, so up to finite number of eigenvalue. Of course, usually in dynamical system, people say this is very important because this is equilibrium, but it's a rank one. Okay, so if you up to this, if you subtract this constant and subtract some of them, the dynamics is governed by this spectrum. And this spectrum has, in fact, this is an infinite dimensional space, which corresponds to the space studied by Flamini and Forni called the space of Orosecal invariant distributions. And it governs the long time dynamics. And what we claim, it looks like a quantum dynamics. For example, it is known for constant curvature. You can compute with a group theory that the eigenvalue here are the square root of the Laplacian. So this operator is conjugated to the wave equation.
All the eigenfunctions, you said the eigenvalue of the first band, they are invariant to the cycle.
In constant curvature, yes. It is shown in a three-dimensional dimension, okay, with some pinching condition with Colin-Guillerbou. We expect in general, but up to now, we are able to show this only in the high frequency limit. So approximately, okay, it's a result that, yes, somehow, yes, exactly. Yes, somehow. Okay, thank you very much for your attention.
Any more questions?
So very naive one. What can you say about the bonds? I mean, when can you say something about when they do not collapse, etc.? And is it very stupid? Is it clear that there is no minus infinite in the interval? Well, things like that. What can be said about these bounds, these intervals?
Yes, when they are separated, okay, we can show that. In fact, most of the eigenvalues here concentrate on the vertical line in the first band, and you have what is called the Weil law. The density for omega imaginary part very large grows like omega power d, the dimension some of a stable direction. We have an equivalence of the density.
Okay, so
like
what you are interested in is in higher.
Yes, we are. So we are interested
higher
only,
imaginary
for this very large, because we use micro local analysis, okay, on this cotangent bundle, and micro local analysis just explain us what behaves for large frequency. We are unable to say something in this region, which nevertheless is very important for dynamics. But for us, it's a finite rank correction. Okay, like we forget it.
Other questions? Okay. If not, let's thank Frédéric again. Okay, so it is a pleasure to introduce Daniele Galli from University of Bologna, and is speaking about the cohomological approach to Ruelle-Pollicott resonances and speed of mixing of Anosov diffeomorphisms.
Thank you, Roberto, for the presentation, and thank you to the organizers for having invited me to this conference. This is the title of this talk, and it is also the title of my PhD thesis. And it concerns, as the title says, Anosov diffeos and Ruelle-Pollicott resonances. The talk is divided into 3 parts. In the first one, I will recall some basic results of Anosov diffeos. In the second one, I will give the statement of my results, and then I will give an idea of my proof. So let's start with this classical definition that probably all of you knows. We have a closed orientable, also connected Riemannian manifold M, and we assume that there is a C1 diffeomorphism such that the tangent bundle, sorry, splits into 2 subbundles, ES and EU, that are both invariant under the dynamics. The vectors of the stable subbundle are expanded of a factor lambda tilde to the n under the action of the dynamics in the past, so they are contracted in the future, while they are expanding, the elements of the unstable bundles are expanded in the future of a factor lambda to the n. In general, this constant appears here, but with a small change of the metric G and also of the expansion factor, we can obtain that the constant is 1. So we assume that we have 1. Some example, the classical, the simplest example of Anosov diffeos is given by hyperbolic automorphisms of tori. We have a matrix in SL and Z, an hyperbolic matrix with determinant 1 and no eigenvalues of modulus 1. In that case, this induces a map on the torus that is Anosov. The stable subbundle is given by the contracting, the direct sum of contracting eigenspaces, and the unstable subbundle is given by the expanding eigenvalues. This does not, there are also nonlinear examples. I put an example here. This is the sum of an hyperbolic automorphism of a torus and a nonlinear part. And this is also another example of Anosov diffeo when delta is small. In fact, there is this famous result of structural stability and persistence of hyperbolicity that says that the condition of an Anosov system is open. And every Anosov diffeo F tilde close enough to F is also topologically conjugated to the initial dynamics F. This does not exclude all other example of Anosov diffeo. We have Anosov diffeos on tori. There are also Anosov diffeos on nil manifolds that are quotients of simply connected Lie groups with respect to a discrete subgroups. And finally, there are examples of Anosov diffeos on infranil manifolds that are constructed with another quotient over nil manifolds. And so every Nil manifold is covered by nil manifold. What's the point of this classification? Is that there are no other examples now of manifolds that admits Anosov diffuse, and it is conjectured that they are all the examples of Anosov diffuse. So there are no other manifolds that admit these dynamics. And in particular, it is also conjectured that every Anosov diff is topologically conjugated to an hyperbolic automorphism on one of these algebraic examples. So the key point of this slide is that all known examples can be read also algebraically in some sense, because there is this topologically conjugation. Okay, we are interested in the ergodic properties of Anosov diffuse, statistical properties. I consider a topologically transitive C-infinity Anosov diffuse on a close connected orientable Riemannian manifold, and I assume that lambda is the expansion factor and lambda -1 is the contraction factor. The dynamics can be nonlinear, so I take into consideration every kind of Anosov diffuse. And I just remark that the hypothesis on topologically transitivity is not so strict because it is also conjectured that every Anosov diffuse on a connected manifold, otherwise it's false, is topologically transitive, so it admits a dense orbit. I'm interested in the ergodic properties of these dynamical systems with respect to the measure of maximal entropy. The measure of maximal entropy is an invariant measure that satisfies this variational principle. So it is the invariant measure such that the entropy with respect to that measure is the topological entropy, and it is the sup on all invariant probability measure of the metric entropy. What's known about these measures and these dynamics? It is known that this measure is unique, exists, and it is unique. And also the dynamical system becomes a Kolmogorov automorphism. And in particular, this result implies also that the measure is ergodic, it is mixing of all degrees. So there is a very chaotic behavior of these dynamical systems. All these results have been proven by classical techniques, the techniques developed by Ruelle, Sinai, Smail, Bowen, that are based on the construction of a Markov partition, and then by conjugating the dynamic of the Anosov system with a subshift of n type, and then studying the ergodic properties of the subshift. Recently, another approach has been developed, studied by Liverani, Baladi, and their collaborators, and it is called a functional approach, and this gave the opportunity to prove stronger result. In particular, we are interested in the speed of mixing and also in an asymptotic expansion of this limit. In particular, they proved, Giusel and Liverani proved that if we restrict to consider smooth observables, there exists a complete, here should be C infinity, I think, yeah, there is a typo. There exists a complete asymptotics for the limit of the slide before. We have that the first term is the product of the two measures, and we have this expansion where the terms xi are called Ruelle-Pollicott resonances, and c, xi, k are bilinear form computed on phi and psi. Notice that since the first Ruelle-Pollicott resonance Xi1, these are all smaller than 1, so this also implies exponential decay of correlation, and the speed of the exponential decay of correlation is given by the largest Ruelle-Pollicott resonance. After this result, a natural question is, okay, this asymptotic exists, but is there a way to identify these Ruelle-Pollicott resonances explicitly? This is just a list of references where there are some attempts and results in this direction. There are in the case they prove the complete set of Ruelle resonances for the SRB measure in some cases. There are also these two papers that concerns the number of Ruelle-Pollicott resonances for Anosov diffuse. There is also another explicit example where the Pollicott and Sewell obtain explicit resonances for Anosov maps of the torus. There is this very recent paper of Faure, Guzel, and Lannot, recent, no, but it is about Ruelle spectrum of linear pseudo-Anosov map, and in that case they obtain the complete asymptotics and all the Ruelle-Pollicott resonances for linear pseudo-Anosov map that is on surface of higher genus. And finally, there is this work of Batterly, Chiamari, and Liverani, where they compute Ruelle-Pollicott resonances in some examples. And the last section of this paper inspired my thesis, because they consider the my two-dimensional case. So the proof of my two-dimensional case was already given by Carlangelo and Oliver and Nilofar. Okay, before giving the statement of my result, I need to recall what is the RAM cohomology. We have the space of differential forms. The exterior derivative gives a co-boundary, gives a cochain complex, because decompose D is equal 0. And by considering the quotient of closed differential forms with respect to exact forms, we can construct the standard RAM cohomology. And in particular, if we consider the push-forward operator acting on differential form, this induces an action on the RAM cohomology, because the push-forward operator preserves closed and exact forms. Okay, now I can state my main result. We assume the hypothesis I gave some slide ago. We have that if lambda 1, lambda 2, lambda m are the set of eigenvalues acting on the ds, the RAM cohomology, where ds is the dimension of the stable manifold, such that they fulfill this bound. So lambda is larger than lambda minus 1 e to the h top, then I can compute partial asymptotics, where the first Ruelle-Pollicott resonances are expressed in terms of these eigenvalues of the action on cohomology. And the error term that I obtain is lambda to the minus n. Okay. From the theorem, I also obtain a corollary about the decay of correlation, because if I have that theta is the maximum between lambda, the second largest eigenvalue in cohomology, and my bound lambda to the minus 1 e to the h top, I can say that the speed of mixing is given by this theta to the n, e to the minus h top, depending on which one of these two values is larger. Yeah? Yeah, it's lambda to the minus, yeah, in the case, because I call theta lambda minus 1 e to the h top. So if you put this second term here, you obtain lambda to the minus n. And this is, no, I will explain you at the end. Yeah, yeah, exactly. You anticipated me, because for every Anosov diff on Tori, I obtained that the maximum among these two values is lambda to the minus 1 e to the h top. That means that there are no eigenvalues in cohomology that are larger than lambda minus 1 e to the h top, except e to the h top. And I mean, the problem is that lambda to the minus 1 e to the h top is a large bound. So it's reasonable that in general there are not, but there could be cases where this yeah, you proved the same result, probably Carlangelo, Giovanni, and you. Yeah. Yeah. Okay. So idea of the proof, the key point of the proof is to study the action of the push forward operator acting on a suitable anisotropic Banach space. The push forward operator, in my case, has the role of the transfer operator. Don't be scared by this definition. I will try to explain you how do I construct my norm. We consider, we consider a differential form H. We apply up to P derivatives to H, and we integrate this differential form against another differential form. This is a pointwise scalar product obtained through the metric against a function that is at least CQ regular. And we integrate this scalar product along a piece of manifold that is close to the stable manifold. I can say that the tangent space to W is in the stable cone if one considers the other definition of Anosov diffs. And so this norm is anisotropic because we are considering we are measuring a direction through derivatives and another direction through antiderivatives through integration. And this different way to compute the norm gives an anisotropic Banach space that is defined as the closure of the differential forms with respect to this norm. Okay. Yeah, and these spaces can be injectively immersed in spaces of currents that are the dual of differential forms, that are the analog of distributions for functions. Okay, I want to prove that, yeah. No, I don't have. Yeah, I don't have examples where there are non-trivial resonances in these annulus. I don't know. Okay. Okay, the standard way to prove the quasi-compactness of the transfer operator is to use, okay, a transfer operator, a bounded linear operator on a Banach space is quasi-compact if the essential spectral radius is strictly smaller than the spectral radius. Roberto gave us an introduction to this property. And the standard way to prove quasi-compactness is this Hamiltonian theorem that says that if we have a strong norm that B is a Banach space with a strong norm, and we have another norm, weaker norm on the same space, if we have that the immersion of the strong space inside the weak space is bounded and compact, and if we have these relations that are Lasota-York inequalities, we have that the operator is, the linear operator is quasi-compact, and there is also an estimate on the essential spectral radius that is given by this factor. Okay, I proved that the inclusion of BPQL inside the BP minus 1 Q plus 1 L is compact. So I have the first hypothesis of Hamiltonian theorem. And also I proved Lasota-York inequality. In particular, the first three inequalities gives the bound on the spectral radius. They say that on 0 and on the dimension M currents, the spectral radius is bounded by 1 because there is no dependence on n in the coefficient, while for intermediate cases, there is this lambda to the minus ds minus L in absolute value. And also, I proved that the second part of the Lasota-York inequalities that gives the bound on the essential spectral radius. And in particular, you can see that there is this factor lambda to the minus n, the minimum among P and Q. And so pushing P and Q to infinity, we can assume that the essential spectral radius is small as you want. So for us, we can assume that these operators are compact in some sense. Yeah? Yeah, they proved this result for distributions. In general, there is a paper of Giulietti, Liverani, Pollicott, where they use the one about zeta functions, where they use these norms for Anosov flows. So I have rewritten the proof for Anosov diffeos. Okay. Okay, so what we obtain as a corollary of the Hamiltonian theorem and our two previous results is that we have this bound on the spectral radius, that is lambda minus ds minus L e to the h top, and in the essential spectral radius there is this factor that push the essential spectrum to the origin to 0. Okay, once we have this, we are interested in the action of the transfer operator on BPQ ds, on the dimension of the stable manifold, because in some sense we are looking to the dynamics on the past through the push forward operator, and so the elements that are more expanded are the one on the stable manifold. This is the idea. So we have that, this is the structure of the spectrum. We have e to the h top, that is unique, simple, maximal eigenvalue. And if we consider the corresponding eigenvector, omega bar, and the dual eigenvector t bar, we can reconstruct up to normalize it, we can reconstruct the measure of maximal entropy. So we can say that the eigenvector corresponding to this e to the h top is the measure of maximal entropy. We can interpret omega bar and t bar as the two Margulis components of the measure of maximal entropy, because the measure of maximal entropy splits into these two directions that are scaled by this factor e to the h top. Okay. Okay, now these Banach spaces are constructed starting from differential forms. So we can try to extend the properties of differential forms, in particular the cochain complex, to these anisotropic Banach spaces. In particular, we have that the exterior derivative is a bounded operator, and the relation d composed d equals 0 continues to be true. So we can define another anisotropic de Rham cohomology that is the quotient of closed currents in this BPQL with respect to exact currents in BPQL. Okay, so I said that we are interested in the investigation of the spectrum in dimension ds. So this is a picture of the spectrum we are interested here. I also pictured these two other circles that represents the spectrum in dimension ds-1 and ds+1, because we want to use exterior derivative to jump from one dimension to another to get some information. So in particular, we are interested in the eigenvalues that are green, because they are the eigenvalues that are in this annulus, which is bounded by the spectral radius in dimension ds and the spectral radius in dimension ds+1 and ds-1. So if I consider an eigenvalue here, I consider the corresponding eigenvector omega, then I can compute the omega, which belongs to b p-1 q +1 ds+1. So it is here, and it is again an eigenvector for the push forward operator. So there should be an eigenvalue here. But this is out of the spectrum. So what we obtain is that the omega must be closed. Otherwise, there would be these eigenvalues. And so we obtain that all the eigenvector corresponding to these eigenvalues are closed. On the other hand, with a quite more difficult proof, we can prove that they cannot also be exact, because otherwise we can find a potential here. Of course, we cannot say that f star u is equal mu u in general, because in general there will be a closed part that does not make this an eigenvector for mu. Of course, if the v is equal 0, we would have that nu is an eigenvalue here. So there is nothing to prove, because nu cannot be an eigenvalue here. On the other hand, if v is different from 0, there are two cases. We could have that f star minus mu ed is invertible on closed currents here. But in that case, we would prove that also u is closed, but du is equal omega, because u is a potential of omega that is here. And so this case cannot be true. On the other hand, if f star minus mu identity is not invertible, this proves that nu must be an eigenvalue also here. So in every case, starting from omega is exact, we obtain a contradiction. And so all these green eigenvalues correspond to closed, non-exact currents. And we can see them in the action on cohomology. Yeah. So nu belongs to the spectrum on cohomology. Okay, once I arrived here, I found, okay, nu is an eigenvalue on cohomology. I want to study the action on cohomology, but I'm working with this anisotropic de Rham cohomology. I'm not sure that this cohomology is isomorphic to the de Rham cohomology. So there is another technicality, because BPQL is not the right space to prove that anisotropic de Rham cohomology is isomorphic to de Rham cohomology, but I need an intermediate version. I need a space such that the element of this space are currents of BPQL, such that its derivative is again BPQL. I don't want to lose regularity. I define this norm that works. And I proved this theorem, almost trivial theorem, that says that they are intermediate version of these anisotropic Banach spaces that I defined before. They have the property that if omega is BPQL, I don't lose regularity when I apply the exterior derivative. The bound on the essential spectrum and on the spectrum are the same. I can construct another anisotropic de Rham cohomology. The previous result, this one, also work when this space is replaced by CPQ ds. But now I know that this de Rham cohomology is isomorphic to the standard de Rham cohomology. So I can get information by just considering the cohomology constructed with differential forms. Okay, so I have proved that these eigenvalues must appear in the standard de Rham cohomology, so the one constructed with the differential forms. In particular, for the torus, it's easy to compute eigenvalues on cohomology, and it's easy to see that there cannot be eigenvalues in this annulus. Just a remark, since e to the h top gives the maximal expansion, in some sense, asymptotic maximal expansion of ds subspaces under the action of this dynamic, and lambda to the -1 is the contraction. When I study the action on the Rham cohomology, it is reasonable that the second largest eigenvalue is smaller than lambda to the -1 e to the h top. So I think that it could be that in any case we are in this situation, and this situation works for any Anosov diffeo. Anyway, this gives an estimate on the speed of mixing, because it says that the speed of mixing is at least lambda to the -1. Once we have this result, I can decompose the push forward operator acting on my Banach space as the sum of this term that correspond to the largest eigenvalue. It is simple, so there is no Jordan block, while I have to consider Jordan blocks for other eigenvalues because they could have higher multiplicity. And there is an error term that corresponds to this operator Q that has spectral ratios strictly smaller than lambda to the -1 e to the h top. After this computation, I obtain that the asymptotic of that I wanted to prove, that is, we have that the correlation function goes as n goes to infinity as this term plus an error, and I conclude. I was too fast.
We have time for questions, if there are any. Okay, just a curiosity is the fact that you look at the measure maximal entropy. It has something to do with the proof. I mean, can you do something similar for the SRB, or it is in principle you could do?
Yeah, there are some partial results of Carlangelo where he studies the SRB, but using differential forms and currents, I don't know.
Okay, so it is really working because you're looking at one
just
potential.
one remark to answer the question probably Vivian asked me before. I cannot go through into the spectrum because I have the problem that I can compose the exterior derivative only one time. Because otherwise, if I could compose D, I could jump from one dimension to the other and so on, and I could arrive to a very small radius. But the problem is that the exterior derivative, when you do decompose D, you obtain always the 0, and this does not work for other.
What about eigenvalue? Can you argue that they are simple, for example?
Yeah.
No, but for example, can you use this to prove that measure of maximal entropy is unique, for example, right? The simplicity of the eigenvalue. Okay.
Yeah, you can use this.
Well, for example, I mean, imagine that in some absurd infranil manifold, there is an eigenvalue that is outside. I mean, it seems unlikely, but then would it be simple or not? I don't know. I mean, that's the question. Yeah, I know it's no, but my question is that can you get it from these arguments? I mean, yeah.
So I don't understand which one you're interested, the maximum or the
Well, I mean, up to now we know only that there is the maximum, right? The other one we don't know if they exist. So I can ask for the maximum, and I don't know.
Yeah, you cannot say something about the multiplicity from the cohomology because you have the problem that if an eigenvalue is in cohomology, this gives you that it appears for the push forward, but the eigenvectors corresponding to this eigenvalue there could be many eigenvectors for the same eigenvalue if you study currents, because if two eigenvectors, the difference between two eigenvectors is closed, then you don't see that in cohomology. They are the same in cohomology, but they are different for currents.
Then they should be exact, right? Because if they are not exact, then it should see them. Yeah, they're simple.
Okay. I don't know. Giovanni says yes. So if they are simple in cohomology, they should be simple.
Okay, hi everybody. We start this afternoon session. The first speaker is Sakshi Jain from the University of Rome, Tor Vergata. She is going to talk on dynamics on non-Markov systems.
Okay. I would like to thank the organizers for giving me this opportunity to talk, and for everybody in the audience for holding on to the conference for this long. And I'll be talking about, as he said, on the dynamics of non-Markov systems, but I would begin with some introductory definitions, which I'm sure everybody knows, but nevertheless, I would write them. Okay. Let me know if what I write isn't visible or it's too small or anything. Larger. Ah, okay. I didn't hear. I'm sorry. So we consider a function t from x to x, which may be continuous and may have some regularity as much as we would want. And similarly, x could be a topological space, could have metric structure or some smoothness structure, whatever we would want. So I would write just a space. And okay. And let's suppose mu is an invariant measure. So that means t star mu is mu. And then I would say that the function is mixing if, well, there are many definitions of mixing, but I would say the function is mixing if there exists a class of functions which is reasonably smooth, let's say. So there exists a class of functions which is, let's say, C, such that for every f and g in C, we have so if this limit is 0, we would say that the function is mixing, and this particular quantity is also called as correlation function, and so the limit tending to 0 is called as decay of correlation as well. It's just synonymous. But so mixing is not a very rare property for a dynamical system to hold, but we are rather interested in quantitative properties. So rate of mixing, let's say, so how fast does this decay happen? And for that, there are few techniques that one could employ. And for example, what we like to employ is transfer operator methods. And transfer operators have already been introduced in previous talks, but I would still state the definition just for that one person who might have forgotten already. Okay. So, okay, sorry. So we have this system, and then for some function phi, which is from x to c, which may also have some continuity, of course, but sorry. Continuity, of course, but some regularity as it is required, or boundedness, or some added structure to it, then I would say that this function L t phi, so it is with respect to the system T, and this weight function phi, I would say that it is a transfer operator, and it is defined as this quantity here, where this is here because this function t might have some discontinuity, might not be 1-to-1, for example. It may have one point may have many pre-images, so it adds on to every pre-image that that a point may have. And here, when so there are some special transfer operators that we generally employ to look at the measures that give us more information about the dynamics as compared to others. For example, if the weight is inverse of the determinant of dt, then this transfer operator is the operator which is called as Perron-Frobenius operator. and it is the one which is associated to SRB measures. So scenario elbow bend measures, and if the weight function is 1, then the transfer operator is the one which is associated to measure of maximal entropy, which was also discussed about in Daniele's talk. Entropy. So yeah, so I was saying that when we have to discuss the rate of mixing or the rate of decay of correlation, we employ different methods, and one of them is transfer operator. And what do we do with it is that we study the spectrum of this operator, and that gives us information about the decay of correlation, or its rate for that matter. And okay. Okay. So to tell you about how do we get information from its spectrum about the rate of decay of correlation, I would like to say a few words about what is essential spectral radius, and that because a few weeks ago I discussed a little lemma about essential spectral radius, and we found out that because there are many very different definitions of essential spectrum, everybody may have their own definition, and we need to agree to one for certain problems. And for me, the essential spectrum is defined as for an operator L, intersection of, okay, I'll just say what it is. So for me, essential spectrum is the one, is the part of the spectrum which stays unperturbed under the addition of compact operators. So it stays the same modulo the addition of compact operators, where so B naught X is the space of compact operators on K. Well, because I said that there are different definitions of essential spectrum in the business, I may as well point out that essential spectrum may have many different definitions, but for all those definitions, essential spectral radius is the same. So, and actually we are more interested in the radius, so we could just ignore different definitions. Okay. So there is some theory about the spectrum of transfer operator and how does it help us in deducing information about the rate of decay of correlation, which says that if, so okay, for example, the spectrum of an operator may look like something which is inside this radius. So let's say that it has a spectral radius which is 1, which is true in case a system is mixing. So 1 is one of the eigenvalues and is the leading eigenvalue after renormalization, of course. And then it may have some point spectrum which may be like this here, and then some continuous part of the spectrum which is basically essential spectrum. And we say that there is exponential mixing. When there is a spectral gap, which we already heard about in a talk in the morning. But what do I mean by spectral gap is that the second leading eigenvalue is, and the leading eigenvalue has some positive gap in between their modulus. And there are some concrete examples of the systems where we do attain exponential mixing. For example, For example, in case of expanding maps, so let's say T is an expanding map on circle, which is a C infinity map. And by expanding, I mean that its derivative everywhere is greater than 1. So this is an example, yes, we'll say. Then there exists a unique invariant measure. Absolutely continuous with respect to Lebesgue. Such that, okay. So as I had said while I was stating the definition of mixing, that there is some reasonable class of spaces C for which this condition holds true. So here that class is W11, so Sobolev 11 space, and we have exponential mixing. So that is sorry. Where lambda is something less than 1. So this is a concrete example where we attain exponential mixing. But then, because mathematicians are curious minds always, they want to know more. And so there is further something that we can say, which is called Ruelle spectrum, or asymptotic expansion to arbitrary precision. So what I mean to say is that we could also find out these pointer spectrum, what are they up till arbitrary precision, and I'll make it clear in a moment. So, okay. So what do I mean by Ruelle spectrum is that that I am able to write this quantity here as okay. Okay. So Ruelle spectrums is defined as the ability to write this quantity here as this. So to decompose it into this term here, these terms here, where lambda i's are complex number with modulus less than epsilon, and I say that for any given epsilon positive, if there exist finitely many lambda i's, such that I could write this quantity like this, and whereCij's are bilinear functionals in FNG, and it is with the error of epsilon to the n. So basically, I mean to say that these lambda i's are the representatives of point spectrum, and that error part is in the essential spectrum. And we say that a system admits full Ruelle spectrum if we are able to do this for any given epsilon positive. We are able to find out finitely many eigenvalues which are lying in there, and we can squeeze the essential spectral radius to as small as we would want, which is possible in a lot of cases, but not always. But let me tell you a lot of work which has been done in this direction, and what are the systems that are known to admit full Ruelle-Pollicott spectrum, which is okay. It is also called as Ruelle-Pollicott spectrum. Okay, and okay, so there has been work by Nod, maybe I don't know how to pronounce, but okay, and they have found out that uniformly expanding piecewise real analytic systems admit full Ruelle-Pollicott spectrum, and then for Guzzel and Lenoux have found out that linear pseudo-Anosov systems also admit full Ruelle-Pollicott spectrum. Also, Bertolli, Chiamari, and Liverani have given full Ruelle-Pollicott spectrum for a lot of systems, in fact. For example, Markov piecewise expanding, piecewise smooth, and actually there's a lot of literature on this particular thing. But okay, so our next interest was to see if we can locate Ruelle spectrum also in case of non-Markov, obviously motivated from the Markov systems, if it is also true for non-Markov systems. Okay, so to tell you what did we find out, I may first introduce what do I mean by non-Markov systems. For me, my function would be an interval map, t from 0, 1 to itself, and then I would say the system is non-Markov if there exists A in 0, 1 such that T is discontinuous at A, of course, and the cardinality of this set TKA is infinite. So in case of Markov systems, what happens is that the function is obviously discontinuous, but every discontinuity has a finite orbit. So after a certain point, every partition starts mapping. Okay, how do I say this? I'm sorry. So there are some partition elements, let's say I1, I2, I3, and there exists an iterate such that Tn I1 contains other partition elements. So it does not intersect absurdly with other partition elements, let's say. Okay. But in non-Markov systems, it doesn't happen. The partition doesn't stabilize, if I may say. It keeps breaking in every iterate. Okay, now to be able to see if we are able to locate Ruelle spectrum in case of non-Markov systems, I would like to make some observation here, which would land us to the result. Okay, now I might have made a remark actually, but I forgot. But anyways, okay, so to be able, while I drew this figure, I was saying that we could squeeze the essential spectrum to arbitrarily small radius as much as we want, but we are able to do that when we increase, in general, when we increase the regularity of the observables. So as much as you increase the regularity of the observables, you can decrease the essential spectral radius and you can locate the point spectrum to an arbitrary precision. And so since we wanted to address the possibility of non-Markov systems admitting Ruelle-Pollicott spectrum, we thought that we may start with the most smooth observables in business and see if we are able to locate them. So let's consider G in C infinity, so the smoothest possible. And okay, so let us say it looks like this, which it may not, but let's assume. And And I try to see the action of transfer operator on this function in case of non-Markov system here. Okay, or I may as well first write. So by definition, L phi g of x would be phi of y g of y, and you may be able to notice that because A has an infinite orbit, the action of transfer operator will give discontinuities at the orbit of A. So as much as you operate with this transfer operator here, you'll keep getting more discontinuities on the orbit of A. So it implies that if no matter how smooth or continuous the function we begin with, the observable we begin with, we have to allow discontinuities on the orbit of the discontinuity that we have already. So to be able to find out a nice Banach space that we could work with, we still have to allow discontinuities on the orbit of the discontinuity. So the first observation is that the Banach space that we might be able to work with has to allow discontinuities on this set. And you may see that the jump is given by phi A and g of A. So this gives us a generation of discontinuity. And there is the second observation, which you may observe that okay, and you may be able to observe that whenever I apply transfer operator on the images of G under transfer operator, I keep getting discontinuity and it gets shifted by this quantity here. So there is a shift in the discontinuity. Yeah. I'm sorry. G is any C infinity function to begin with. It is the phi. The jump, I'm sorry, yeah, okay. So this is the jump of function. So for example, jump at A. So if I have a function f and I want to say, I want to see what is the jump of this function, then it is basically the right continuity. Okay, I'm sorry. I should have said this. Okay. So as soon as we see that there is a shift in the discontinuity, we know that we cannot have as good a description of a spectrum as it is given in other cases before. So it lands us at our first result. Maybe I forgot to say while I began with the talk that this is based on a joint work with Oliver Butterly, Giovanni Canestrari, and myself, and we are all in University of Rome Tor Vergata. Sorry. Also, being new in the business, I don't understand if I should write 23 or 22. It was published online 22, and Okay. So we have this non-Markov system, which is piecewise C0 monotone. And the weight function phi is piecewise C0 and bounded. Then for the Banach space B, which I'll write what properties does it have. B, which which has these properties that C infinity is contained in B, and that is basically, as I said, that we begin with the smoothest possible observables to be able to land at a good description of spectrum. And so we allow all the smooth observables inside, and then L phi. So the transfer operator must be able to act on this Banach space, obviously, to be able to talk about it. So L phi extends to be a continuous operator on this Banach space. And I didn't write this. And that it bounds the L infinity norm. So for every H in the Banach space, we had to have this condition that the L infinity norm is bounded by the norm in this Banach space. Then if there exists a non-trivial discontinuity, which means that the function is non-Markov, so there exists some A in 0, 1 such that it has infinite orbit. Then we found out that we cannot make essential spectrum as small as we want, which was our first aspiration actually. Then there exists a lower bound of the essential spectrum. So the essential spectrum of L phi restricted to B this quantity here, which I may write exactly what it is here. So it says that the result says that if we have a non-Markov system, then for any reasonable Banach space, there is an essential spectrum that persists. So we cannot make it as small as we want. There is no matter how smooth the observables you begin with. So we cannot, in other words, we cannot have Ruelle spectrum to arbitrary precision as we wanted at first. And I would like to talk about the idea of the proof, but before that I may give some historical perspective. Okay, so obviously we are not the first who thought about this thing, this system. There has been a result by Keller in 1984, which says that for any function piecewise expanding, he works on BV spaces, so the bounded variation spaces, and the weight for him is the one that I said is associated to Perron-Frobenius operator. And he found out that the essential spectral radius is in fact equal to, so the BV norm is in fact equal to this quantity here, which I may call as lambda k, k for Kähler, and yeah. Yeah, and also in here. Yeah, thank you. Yeah, so Keller has this result, and this is exactly the essential spectral radius in case of BV functions and this weight. And we obviously wanted to see if our result is any better than this. We are adding anything to the system, or we are doing nothing really. And so we wanted to find out if there exists any system for which our quantity is better than this quantity here. I don't know, maybe, okay. So, okay, so the question was if there exists any function t such that the bound that we have found out, so lambda in the similar environment, so t1 over t prime is strictly less than Keller's radius, and which lands me to the next result, which is more an example, I would say, that for every c in 0, 1, there exists t, a function, such that greater than equal to c. So not just that our bound is smaller, but it can be made as small as we want within a range of 0 and 1. And the construction is not as difficult, so I may as well write it. So consider this function that I'm trying to draw here. Okay, so it has 4 branches with slope alpha, and of course this is 0, 1. These 2 branches with slope beta, and this is a branch with slope rho, say, and where alpha is of order 1. Of course it is greater than 1 because we are in the expanding case, but it is almost 1. Beta is of order infinity, and rho is chosen in a way so that the orbit of 1, so I'm sorry, because this is orbit of 1, this is the image of 1, so rho is chosen in a way so that the orbit of orbit of 1 doesn't belong to this part here. So for any value of k, tk1 never visits this portion here. So it stays in these 3 bits. Okay. Now let's calculate what would be Keller's estimate. Now you see, because where was it? Yeah, okay, here. So because Keller's estimate is 1 over Tn prime, so it kind of considers the least expanding bit of the function. And for that reason, his bound would be 1 over alpha, which is again of order 1, because alpha is of order 1. Of course, it is less than 1, but is of order 1. And if we consider our bound, we know that what we calculate is for the non-trivial discontinuity. And by definition of this system, the non-trivial discontinuity is 1, which visits only these 2 bits and not this one. So it would be 1 over beta. But since beta is of order infinity, it would be of order 0. So there's a difference of a quantity within 0 and 1. So we can see that it is much smaller than Keller's bound. Yeah, TK1 doesn't visit this this branch. It only sees these 2 branches, for example. Okay, and I don't know how to write this in symbols actually. That's why I left it like this. Yeah, okay, yeah. Thank you. And now I may give the idea of the proof of this theorem. Yes. Okay. So as we know that we allow the most regular functions in our space, let us consider A naught to be, and of course we also observed that not just the most smooth functions, but we have to allow them with discontinuities on the orbit of the discontinuity that we had began with. I think I rubbed the image, but let's suppose we all remember this. And okay, so A naught is the space which is the span of so it is images of the smooth functions under Elphi. And since it may not be Banach space, it may not be complete, I consider A to be the completion of this space. Then we may observe that, okay, let lambda be such that mod lambda is less than our quantity lambda infimum. Been A naught, then so okay, let me invoke the proof somehow. So what we tried to do is that for any lambda which is within this range of the lower bound for essential spectrum that we have claimed it is so, we tried to find out the eigenvectors for this thing. So we will be able to prove that for every such lambda, it is an eigenvalue. So it is in the continuous part of the spectrum, and it contributes to the essential spectrum. So I'm trying to write down the possible eigenvectors that could play the role of eigenvectors for every lambda here. So I define L lambda H to be this quantity lambda to the K over this product and jump at TIA, jump of LH at TIA. And then I claim that it is an eigenvector for a certain operator that I will write now. Okay. So what we hoped to be able to find out an eigenvector for the transfer operator that we are considering, but not quite, like it didn't happen quite as it is. So we found out the eigenvector for some other operator. So let's consider an operator which is called K. Okay, and it is defined, it is a compact operator. It is defined as K of H is phi of A, H of A. So it is compact because it is one dimensional. And then I define another operator. L minus K, and we found out that M star of L lambda H is lambda times L lambda H, which means that lambda, and this is true for every lambda, such that mod lambda is less than this infimum. So it implies that lambda is in the spectrum of M star, but spectrum is the same for the dual and the operator. So it is also in the spectrum of M. Now, when I gave the definition in the beginning, when I gave the definition of essential spectrum, I had said that it stays unperturbed under the addition or subtraction of a compact operator. So it means, okay, oh, maybe I should have said, okay, first that because it is true for every lambda which is in this within this radius, it contributes to the continuous part of spectrum. So it's not point spectrum, it is rather essential spectrum of this operator, right? So it belongs to essential spectrum of M. Now, because M and L differ by only a compact operator, it implies that lambda also belongs to essential spectrum of L, basically L phi, the operator that we were working with. And so it implies that the disk of radius lambda n is contained within the essential spectrum of L phi. And so we cannot, and this concludes basically the proof in a very simple setting, but it says that we cannot make essential spectrum as small as we want, as opposed to other cases that I had stated before. And okay, and then we wanted to see if we can in fact find out some Banach spaces which realize the bound that we have given. So if there are Banach spaces for which the essential spectrum is equal to, or let's say close by our bound that we have given. And to address that, I would state the next result. So for any function t, which is again on the unit interval, but is piecewise C infinity monotone, and uniformly expanding. So maybe we all could notice, actually, right before I rubbed this part, but for this theorem, I did not assume my function to be an expanding function. It could be just C0 monotone. But to construct the Banach spaces that we want, I am considering it to be uniformly expanding. The weight function is piecewise C infinity again, and is uniformly bounded away from 0. Then, yeah, so we were not really able to construct Banach spaces which actually realize this spectrum, this essential spectrum, but it is true for, nevertheless, for every lambda tilde which is strictly less than or equal, less than, greater than. There exists a Banach space B such that yeah. So, okay, one more thing that we may all notice here is that here the quantity is lambda supremum. So it is limit supremum of the previous quantity here. Yeah. So the lower bound is given by limit infimum, and the spaces that we construct are they have essential spectrum close to lambda supremum, but anyways it kind of asserts that there is essential spectrum which is persisting, and that's what we want to see. Okay, and the proof of this theorem is a bit technical, and I'm not going to write the proof, but I would just say a few words about the construction of Banach space and basically the norm. How did we construct the norm? So you may see that all this feature of this system are persisting basically because of the non-trivial discontinuity that it has. So and it enforces the observable also to have discontinuities on the application of transfer operator. So we may as well we anyway have to consider a Banach space for which the norm addresses the existence of discontinuities in the observable. So the norm is given by so I say that the norm is given by the sum of two norms, where this is called, we call it as continuous part of the norm, and this is the jump part. Where the continuous part is defined as and the jump part is defined J zeta, where this norm J zeta norm is given by where these weights zeta k is given as this thing. Okay, it may look a bit scary, but let's just have a closer look at it. So this is the continuous part of the norm, and this is the jump part where the derivative, you may wonder, how do I take the derivative? So it is basically the derivative of the jump part is given by the sum of delta functions, and the absolutely continuous part is the normal derivative. So I divide the derivatives within the two parts, and here the weight is so because of the okay, I have deleted a lot of important things that I should have kept, but these weights come from basically the shift in the discontinuity. So if you remember, it used to get multiplied with the image of phi at the discontinuity points, and that is why it persists here, and it helps us with the construction of norm. And with the use of these norms, we could construct a Banach space which satisfy which actually helps us assert that there is an essential spectrum which has essential spectral radius close to this bound. And yeah, I may stop here. Thank you.
Okay, we resume our session. Our second speaker and last speaker of the day is Daniele Smania from the University of São Paulo. He's going to talk about transfer operators, atomic decomposition, and Besov spaces.
Thank you very much. That's my first time in Pisa, so thank you very much for the opportunity. So I'm going to talk about relations between Besov spaces and transfer operators. So you heard a lot about transfer operators. I'm going to talk a little more, remember some stuff, but in the previous talk, you see a lot about my introduction about transfer operators. So suppose you have a piecewise expanding map. So that means the following, that means that you have a metric space, something like this, and you have a partition of this metric space in a countable number of pieces. Let's call it xi, and each one of this xi, you have a transformation that maps this xi. Well, you have this map. In each one of these guys, you have the map is really nice. Let's say a homeomorphism, something like this. And in each one of these parts, the map expands distances. That means that there is some lambda I that may depend on the piece that you're considering, where you have expansion. So you have that Tx, the distance between Tx and Ty expands by at least a factor of lambda y by one iteration of the map inside this PC, okay? So another thing that's quite important is that usually, as you see in the previous talk, piecewise expanding maps can be extremely complicated dynamics with infinite many periodic orbits, invariant measures. Is really, really complicated. So what you try to do is to understand this in the measure theoretical point of view. So usually you have a reference measure in this space. So I call it this reference measure M, okay? Yeah, every one of those is bigger than one. Yes. So yeah, I'm not saying nothing now about it, but you're right. Usually in the interest situation, this is bigger. Okay, let's put this to make everybody happy. So the infim of I is bigger than one. Okay, so suppose that you have expansion and you have a reference measure M. So maybe this map is not really defined everywhere. There's some set of zero-Lebesgue measure where the map is not defined. You don't care with respect to this measure, okay? So what you wanted to understand is how measures that absolute continuous with respect to this reference measure behaves when you iterate this map. So suppose you have a map, some function rho that belongs to L1, is integrable with respect to this measure. So you can define this measure like the measure with this density that's absolute continuous with respect to M. That's just the integral of rho with respect to M in A. So that's the measure whole M. So it turns out that in the interesting cases, you have the following. You have, I can consider the restriction of this map to the species. You have something like this. And usually the assumption that you have is that this species preserves the absolute continuity of the measure when you act as a push forward of the measure. So we pick the push forward of the measure. I never know if I put the star in the top or in the bottom. So let's put in the top. If you pick the push forward of this, you get a measure that's absolute continuous with respect to the original measure. So that preserves the absolute continuity of the measure with respect to M. So in this particular case, you can talk about the Jacobian of each one of these pieces, Ti, and you can define the transfer operator, Ruelle transfer operator. Operator that is just, if you pick some function phi and you apply in some y, this is just, is exactly as in the previous talk, you just pick all the possible, I'm just writing a slightly different way, you pick all the possible pre-images of this point, and you have some g here, and you calculate it, multiply by phi x, okay? Where this g is just the, this jx is called the Jacobian of t, and g that exists because it preserves the absolute continuous class of the measures. So this g is just 1 over j, something like this. Okay, so you have this picture, and this operator is super nice, super well known. You know that, for instance, that preserves is a bounded operator in L1 of this measure M. So let me just say, I'm not going to talk about this, but you can consider just in an abstract point of view these operators. You can choose whatever you want for G and whatever you want for T. And you can ask about if this preserves some functional space or things like that. People in analysis, harmonic analysis, study this kind of a lot. How, for instance, you can ask if the cohomological operator of some map preserves some space of functions. It's a totally abstraction, it's not related with dynamics. Okay, but I'm concentrating in dynamical systems here. And in this case, you have the norm in L1 of this is actually 1. And indeed, if the function is non-negative, you know that the norm of this guy is exactly equal to the norm of the original function in L1. Okay? And as in the previous talk, I'm going to use this operator to understand the dynamic ergodic theory of this map. Okay, this is heavy. Okay. So what you do is the following: you use this transfer operator, and instead it seems that there's nothing to do with the ergodic theory, but actually, if you know spectral properties of T, of P, usually this implies, I'm going to be more precise, you get the statistical properties of on some Banach space of functions, space B. So suppose that P preserves this Banach space of functions, and you know something about the spectral properties of these, how the spectrum looks like. So usually this gives you, often this gives you something about the statistical properties of observables on this space. Okay, I'm going to give some examples. So let me give you an example of a statistical a spectral property that you usually have. You already talk about this property a lot. That is the quasi-compact property. So suppose you have a functional space, a space of functions that's preserved by this transfer operator. And well, we have one there, right? L1. So L1 is preserved by this. But turns out that the spectrum on L1 is terrible. So what you have is that the spectrum Well, the spectral radius is 1. So you have, but actually the whole unit disk is the spectrum of this operator in L1. So if we pick this in L1, this is the whole unit disk quite often. So there are lots of examples of this. Probably is true in, well, it's a very abstract nonsense argument, and you prove that the spectral radius of this is, sorry, the spectrum is the whole thing. And this somehow reflects the fact that L1 observables in general has terrible statistical properties. Okay, so you don't have like exponential decay correlation, central limit theorem for arbitrary observable in L1 in this setting. Okay, so they usually the most nice kind of operator in infinite dimension is when this is a compact operator that I'm not going to define, but the main property of these compact operators is that the spectrum is super nice. It's like basically like a matrix in finite dimension. So you have the unit circle here, and you have just a finite number, countable number of eigenvalues with finite, the generalized spectrum is finite dimensional, and maybe they're accumulating at 0, but that's it. Okay, so this is a perfect situation because you can use, behaves much, well, in a very nice way, pretty much close to a matrix in finite dimensions, but this is very rare. So this is extremely rare. There are some situations, real analytic maps, expanding maps on the circle, where you have this property. Ruelle has some papers about this and others, but that's very rare. Okay, so that's an ideal situation, but it's very rare. So there is some intermediate status situation here when you have a functional space where this is quasi-compact. When you have a quasi-compact operator in this guy, the spectrum somehow mixture these two behaviors. So you have again the unit circle here. You have some isolated eigenvalues here, and you have a very strange word part here. That is the sensory spectrum that you heard in the last talk. So these two guys actually are extremely sensory spectral radius. Sensory spectrum, and this is extremely weird, and you cannot control that much. I don't know how to write weird. Okay, is it strange? Strange. Is it strange? Okay, super strange. So you cannot control this. Extremely strange, but for most very nice statistical properties of observables is enough to know that the spectrum close to the unit circle is super nice. Okay, so this is enough for a lot of nice results. So let me just complete this picture. Say that another way to see quasi-compactness in this setting where the spectral radius is 1 is that this operator you can decompose in the sum of two operators, contraction in this space, and this is a linear operator which has finite rank. The image has finite dimension. I'm not sure if this is equivalent, but this certainly implies that's quasi-compact. Okay, so that's the kind of thing that you need. Okay. Well, we need an iteration of K to be a contraction, not K in itself, but it's pretty much the same thing. Okay, so if you have this nice spectral property, that's quasi-compactness, then there's a lot of tools that people have been developed in the last 40 years, maybe 50 years, where if you have the quasi-compactness of the operator P, and you can deduce a lot of things with some additional assumptions about your expanding map. So if you have you can prove the existence of absolute continuous invariant measures. And actually in this case, you prove usually that the density, you know something about the density belongs to this space. Okay. Other thing that you can usually prove with additional assumptions. So there's always maybe some additional assumption on some of these implications. You have exponential decay correlations. for observables on this Banach space of functions, okay? But you need, like, say, topological mixing or some additional assumption to conclude that. Not going to talk about that. And another thing that sometimes you obtain is central limit theorem. For a class of observables. I cannot be more precise in general for this. You don't necessarily have, can conclude a central limit theorem for observables on B, but in multipliers of B with certain additional properties. So I'm not going to give the details. For instance, if B is an algebra, usually you conclude that the elements of the Banach space satisfy central limit theorem. Okay, and again, this particular takes a lot of time. Okay, so you can, these implications are not trivial at all, but there are lots of technology that you can use in the literature to prove the things once you have quasi-compactness. Okay, so that's why in some this is a course about stochastic dynamics, but sometimes there's no stochastic at all in these lectures because people concentrate in this part that usually take a lot of time. This is a hard work to prove the quasi-compactness of this operator. And then they take maybe a few pages, but you can deduce these things, okay? Sometimes, yeah. Yes. Yes. So no, so in this setting, the set of piecewise expanding maps is a space of functions. Is a space of functions, but the regularity of these functions can be very different depending on the regularity of your map. For instance, I'm going to give you a list you're going to see. So there are many examples of this space of functions depending on your dynamical system, okay? So actually the whole job is to find B. So yeah. Yeah. So the whole job is to find B. Okay, so once, okay. Yes, okay. Okay, so another thing that appears in all these lectures, many of these lectures, is Lazota-York inequality. York inequality. I'm not sure if it's correct to say that this is a spectral property. It's more like this implies some spectral properties of the map. So let me say what's Lazota-York inequality. I'm going to just state, to define Lazota-York inequality, you need two Banach spaces. You need a space L, let's say, in my case, it would always be L1, but you can talk about Lazota-York inequality for other spaces, and another space of functions B of more regular functions. So B is contained in L1 and usually is compactly contained. So the ball is compact in L1, or something like this. Okay, so you say that you have the Lazota-York inequality if there is some lambda between 0 and 1. Remember that there are no, I'm assuming that the respective radius is 1, and there is some C positive, so that you have that this operator satisfies this inequality here. This inequality here. Okay, this looks very strange, but a way to what is nice that people know a lot of time ago. I think this is Marinescu-Ionescu that I don't know to write down, so I'm not going to write down. They proved that Lazota-York inequality implies quasi-compactness on B. I mean, like a little bit because you just you need some additional assumptions like this is dense in L1, you have a compact inclusion, and so I'm not going to give you the details. So if you have Lazota-York, great, you get quasi-compactness, but you get more things. That is like the dynamics of the Frobenius operator is attracted by the on L1 is somehow attracted by the dynamics in B that's smaller. Okay, so let me just, I don't know how to state that in a precise way, but I can give you some examples. For instance, if you have a Lazota-York inequality, there is an abstract nonsense argument that say something like this. If you have some map, some function in L1 that's invariant by the Perron-Frobenius operator, automatically using this is an exercise. Actually, you prove that this guy belongs to space B. Okay, so you get a lot of information about the regularity of the density. And actually, if you have some lambda here, where lambda has modulus 1, we also conclude the same thing. Okay, so that's just one example of how you can use. There are too many lambdas. Okay, the problem is that I don't know the name of all Greek letters. So let's put alpha, and alpha I know the name. Alpha is equal to 1. This is whole. This whole. Yes, looks like beta, right? Sorry. Okay, so why do you care about this? Because once you have some information about the regularity of the density, you have something about the regularity of the support of the measure, for instance, and then you can use topological information about your dynamical system to conclude measure theoretical things about your dynamical system. So, for instance, if you use this kind of trick, usually topological mixing implies automatically, the topological property implies, well, it's not automatically, but you can work out and prove that exponential decay correlations. So this is a topological property, and using this Lazotte-York inequality, this kind of tricks, you prove exponential decay correlations, because this gives you information about the spectrum, the spectrum, or the stream spectrum of the guy. Okay. Okay, super. That's an introduction. Okay, so now you ask me about what kind of functional spaces you have in this kind of thing. So we have lots of examples. I'm going to give now a few of them. It's not an exhaustive list, but it's a very, I think, representative list of the kind of functional spaces that appears in this kind of business. So let me just check how much time do I have, because I speak very fast. 40 minutes, okay. Okay, good. Okay, so you have many kinds of expanding maps, extremely a long list of examples of expanding maps that appears in literature. So I'm going to do a list here. So I'm going to put the dynamics here. All kind of dynamics I'm looking at. I'm going to put, no, that list is incomplete. I'm going to put the potential here. So the potential is basically G, the Jacobian, right? Is something about the regularity of the Jacobian, or 1 over the Jacobian, or maybe log of a Jacobian. I'm not going to be specific, okay? You have lots of phase spaces. I said that's a metric space, but sometimes you have additional structure in the phase space. You have the reference measure, that's M. And you have also the spatial functions B, where you have Lazotte-York, or spatial functions. B, where you have quasi-compactness. And yes, and you have, the question is, you have in this space Lazotte-York. So that's the question. I'm going to answer yes or no. And yeah, that's it. So let's start with the most traditional ones. The most traditional one maybe is one-dimensional Markovian maps. Markovian maps. Let's say C1 plus beta. Okay. So the most boring example is just map like this. Something like this. Okay, so this is a Markovian map. And in this case, the potential is just log of a derivative. This is holder potential, is a beta holder potential. So the Jacobian is holder. The phase space is the interval in this case. The reference measure is just the Lebesgue measure. And in this case, the most classical example, you have the spatial functions where you get quasi-compactness is a space of holder continuous functions with some exponents beta. I suppose the beta should be a little smaller than this beta actually, but you got some space of holder functions, okay? And then you get Lazotte-York in this setting, okay? In which branch you have, yes, is holder in each branch. You're right. Let me write, okay, on XY, that's what you mean, okay? Okay, another classical example. So this is very old. Okay, historically, this came first. I think the first example is the Gauss map. This actually is not expanding. I think there's one point where you have derivative 1, but the second iteration is expanding. So the Gauss map was the first example that appears in this list. One-sided shift is another example. This is also Markovian map. And who proved this thing is Ruelle, of course, in the 60s, that introduced, I think, thermodynamic formalism for one-sided shift maps. So in this case, the potential is a holder potential too. Okay, the phase space is much more, have a much more weaker structure. It's just a counter set, is some space of symbols, something like this, right? So this is a counter set. The reference measure is not, Lebesgue measure doesn't make sense in this setting. So we have something called an eigenmeasure that I'm not going to explain. Eigenmeasure for this potential. So this, in this case, the reference measure changes with the potential that you have, okay? And in this case, the space of functions is also holder, on which is holder in the whole thing. And yes, and then yes, you have Lazotte-York for these guys. Okay, this list is very big, so let me skip some of them. Okay, so things became, started to become maybe more interesting. More or less in the very year that Ruelle introduced the term of formalism, Sinai introduced Markov partitions for a lot of hyperbolic dynamical systems. And using that, you can use this technology to understand, let's say, Anosov maps or something like this. Some results about Anosov maps. Another class that appears very early is expanding maps on manifolds, more dimensions. This is actually appears in Mike Schub PhD thesis. He studied this in the topological point of view. So in this case, the potential is, I don't know, holder also. You have, this is a manifold. This is a volume form, some volume form there, Lebesgue measure basically. And this is holder, space of holder functions. And yes, you have Lazotte-York on this thing, okay? So things became more interesting when all these maps are Markovian maps. So they preserve some partition. The image of this partition, of element of this partition, is a union of elements of the partition. So this is a Markovian map. And things became more interesting with Lazotte-York and Keller and Hofbauer, when they start to study piecewise monotone, piecewise expanding maps on the interval. Expanding maps. I think the regularity about the derivative is a little different from the two results, but let's put here C1 plus bounded variation. That means that the derivative has bounded variation, okay? So in this case, because you have discontinuities, functions, spaces of continuous functions are not, is not Markovian. Spaces of continuous functions like holder functions are not preserved by this anymore. So it's not even L-defined as operator in these spaces. So you need wider space. So in this case, the space, the potential is BV. Here you have an interval. Here you have a Lebesgue measure. But I know that Keller and Hofbauer also study more general potentials, but I'm going to keep just with Lebesgue. And in this case, you can consider the space of bounded variation functions. And yes, you have indeed laws of York in this case. So all of this is, well, this is not one-dimensional, but it's Markovian, it's nicer. And the rest is all one-dimensional. So you can ask if you can do something with piecewise expanding maps in more dimensions, and then things start to get a little complicated. What happens is that people start to work, let's say, with C1 plus C2, piecewise C2 maps, expanding maps on manifolds. So there are lots of names here, but I'm going to see it Boyaski. I hope I know how to write this. And Coyonson. So there are lots of independent work in this, a lot of works in this setting, okay? And in particular, this case, I think, is C1 plus beta is less regular than C2. So in this situation, you have that the space, the potential is the holder or C1, okay? Here you have a manifold. Here you have a Lebesgue measure. And here you have entrance spaces. So when you have like a C1 potential, you use the space of bounded variations on manifolds. If you ask me what is this, I don't know. So, and there's, in the case of C1 plus alpha, there is this nice Keller space. I think people somehow call it a generalized oscillation spaces or something like this. So it's Keller space. So Keller used this for the first time for one-dimensional dynamics, and then Suso used the same space to understand multidimensional case. Okay, so in this case, you have Lazota-York, yes, but it's conditional. So usually you need to verify some condition. That's the thing about higher dimensions. When you have higher dimensions for piecewise expanding maps, not always you have a absolute continuous invariant measure, and things get complicated. So, well, it's complicated. So you need some assumptions that to verify to have Lazota-York, but turns out that this is generic. So Coyonson proved that for generic piecewise C2 with C1, C2 borders, something like this, you have this condition. Okay, so as you can see, there are many situations with many different Banach spaces. Okay, so so what I propose is to do the following. What I'm going to do, I think I'm going to write here. Yes, this is 2000 here, right? Yeah, there are other results. For instance, Nakamo and Sakamoto for Besov spaces in expanding maps, and Tomini. I don't want to, so let's put Tomini. For piecewise expanding maps on manifolds, and then here you consider Sobolev spaces. And of course should be conditional too. But I'm sure that you can do generic result here too. And you also have, so this is also for piecewise expanding maps on manifolds. And there is a result, maybe I should put here, that's more recent, for piecewise expanding maps, for expanding maps on manifolds here. You can consider another spaces that's much wider that are Besov spaces. This is just expanding. There's no jumps and nothing. There's no discontinuities. So you can actually get Lazotti arc for Besov space that's much wider than Holder spaces. Okay. Okay, so my proposal is to prove the following. I'm not going to prove it, but I'm going to state the result that you prove. By the way, this is a joint work with Alexander Abieto. You can find the preprints in the archives. You define a Besov space. Besov space on phase spaces X that are general, very general, and includes all the cases that I cited before, all the phase spaces that I included before. Okay, so on a very general phase space X, where n we obtain conditional Lazotta-York inequality for piecewise expanding maps on this X. So this X could be a Cantor set, could be a symbolic space, could be a manifold, could be an interval. So it could be many things. Okay, so this is actually a family of Besov spaces. I'm going to define these spaces now. So there are three parameters. So this S is some number that's pretty much the smoothness of the functions. So this goes for 1 to 0 to 1 over P. P is a parameter that goes from 1 to plus infinity, and Q goes from 1 to infinity. Okay. No, you can consider. Well, I need to think about it. I think in the paper we just write for the Lebesgue measure. Yes. Well, I didn't do it. I did just for Lebesgue. Okay. Okay. So what I'm going to do and show you in this case is what you have is the following. For instance, in this case, the most boring Markovian cases, you get a Lazotta-York for all S between 0 and or P. So the S depends on the regularity of the map, okay? But the P, you can pick whatever you want between 1 and plus infinity. The same with the shift. The Q doesn't play a part of this, could be probably anything that you wanted to. Expanding maps on manifolds, you can do the same, Markovian. So when you have a piecewise expanding maps, then you need to be more careful. You need P equal to 1, P close to 1. Okay. And in the same case here and here. Okay, so in all these cases, P is close to 1. P here no, here's Markovian. No, so this is P equals 1. So piecewise expanding maps. Okay. Yes. So it exactly coincides in the case of manifolds and log of derivative. This coincides with the Besov space. Okay, it's exactly the same. Okay, so now in the time that I have, I wanted to give you idea how this space is, and if I really have time, I don't think I'm going to have time. I'll try to show you why these spaces are interesting. Okay, to study transfer operators. Okay, I have 20 minutes. So how you define these Besov spaces, okay? To define these Besov spaces, I just need a measure space. So X is going to be a measure space. Let's say a complete measure space. Let's suppose that you have the reference measure, and let's suppose, to simplify the notation, that the measure is 1. The total measure is 1, okay? So I need finite partitions, a sequence of finite partitions in this space. So we have an infinite sequence of finite partitions. Any one of these has finite number of elements. And X is the union up to a set of zero Lebesgue measure of the elements of each one of these partitions. Each one of them are partitions. And I need these partitions to be regular in the following sense. I need that when you pick an element of the partition of level n, you may have some elements. So there are finite partitions. So you may have some number of elements inside in the next level. And what I need is that there is some lambda 1 and lambda 2 between 0 and 1, so that the measure of P is not very small compared with the measure of this guy. So this is the child, this is the mother. So you need that this guy is not very small compared with the mother. So you have this is smaller than lambda 2 and this is smaller than lambda 1. Okay. So it's very easy to find examples of this. So that's the structure. You don't need a metric structure, you don't need topology, you don't need anything of this. You just need a measure theoretical structure. Okay. So in this setting, I'm going to define the Besov space. But before that, let me give you some examples. So the simplest example would be you pick the interval, 1. So suppose you wanted to understand dynamical systems, piecewise exponent dynamical system interval. You just divide, this is the first element, it's just the whole interval. The second partition you just divide by 2. Then you divide by 4, and so on and so forth. So that's the sequence of dyadic intervals. So this is a example of this structure, okay? You can do, of course, the same with squares. You pick a square, divide in 4, then divide in 4 again, in the same area, and so on and so forth. You get exactly the same thing. If you have a manifold, a compact manifold, you can start with a smooth triangulation of this manifold. Doesn't matter what triangulation it is, just need to be smooth. And you just start to refine this triangulation over and over again in a proper way to preserve this property. Okay, so this is very easy. You can do the same this for like polyhedrons or polygonal regions. You can do exactly the same kind of trick. You just pick refine triangulations and you get this. Okay, there's one more. There's one example that's maybe not so trivial that I can do actually something similar to that in a very much more abstract setting that are alphas regular. Alphas, I don't know how to write alphas regular. So that's the name of alphas up to permutation of letters. So alphas regular metric spaces. So in this case, you have a metric space, a metric D in a measure M. And you have that there's some R naught positive, so that for ball is smaller than this diameter, the measure of this ball is comparable with the radius to the power D. D is the dimension of the thing. Okay. So in this case, so the manifold with the Lebesgue measure is an example of this, a compact manifold. The interval is also an example of this. So in this setting, there is a general result by a guy called Christ. It's a very famous result in harmonic analysis. that is, it's like 3 pages long. It's not that, it's elementary. There is a sequence of partitions satisfying these properties. Now, these are just examples. Most of the examples there are for regular metric spaces, but there are examples in the shift where they are not. Okay. Yes. So that's the answer. Okay. Okay. Actually, if your metric space is a doubling space, that I don't recall the definition, you can change the metric in such a way to get a for regular space, and then you can do exactly the same thing. You need to change the measure. You preserve the measure, but you change the metric, and then you get alpha regular space. Yes. That's true. That's true. Okay, so let me just give you an example where it's not necessarily, I think, alpha's regular space. Is you pick a symbolic space. Let's say 0, 1 with 2 symbols. And you pick this partition, of course, the sequence of cylinders. Cylinders of length n. And suppose you have a holder potential. And you pick m, the eigenmeasure. Measure of this potential. Then in this case, this measure with this partition satisfies these properties. Okay, it's really easy because it's an equilibrium state. This measure is like an equilibrium state, and you can play around. Okay, now you know the structure that I need. That's the structure that I need. I call it these measure spaces with good grids. And what you can do now is define Besov spaces in this space, in this phase space. And again, this definition is very, very, I would say, very elementary. I'm not saying simple, but very elementary. And suppose you put S smaller 1 over P bigger than 0. P 1 plus infinity, and Q 1 plus infinity. So I'm going to say that our observable belongs to this Besov space. If you only if, you can represent this like a composition of atoms. So that's the atomic decomposition in the title. So suppose I pick an element of the partition, of some of this partition. I can define what I call it a Sousa atom. Sousa is the name of a mathematician that used this for the first time in the 80s. I'm going to define a function, call it AQ. That is the following. This function is 0 here and is constant inside Q. Something like this. It's totally a boring function. So it's just 0 outside Q and has a fixed value inside Q. This value is just the measure of Q to the power S minus 1 over P. Okay. So if the measure of Q is large, this is like something like this. If the measure of Q is large, if the measure of Q is small, it's something like this. Okay. So the graph of these functions are like bricks. So what you can do is you say that this function belongs to this Besov space. If you can decompose this function as a infinite linear combination of these atoms. So you have atoms for every level, K. You have elements in the partition. For each element of the partition, you have an atom. It's a countable number of them. And you are allowed to make linear combinations of this. So if you can write phi in this way, and the cust of this representation is finite, I'm going to define the cust. So the cust of this representation, this depends, of course, on P, S, Q, and Q. If the cust of this representation is finite, this belongs to this Besov space. And what is the cust of this representation? It's kind of simple, actually. So this is like Fourier transform. You separate the signal in frequencies in many levels, and now you need to calculate the contribution of each band of frequency to the construction of phi. Okay, so how you do that? You just calculate the size of these guys using the LP norm first. So you just calculate these guys. So this is the contribution of this band of frequencies for the construction of phi. And then you sum of all the band of frequencies and Q here, 1 over Q here. So that's the cust of this representation. And you say that this function belongs to this Besov space if this cust is finite, if there is a representation where this cust is finite. Okay, so once you have this, yes, the whole of S is used to define this height, okay, the height. Yeah, you're right. Here, the norm is always the same, right? But the atoms that you pick are different. Okay, so now you can define the norm in this space. The norm in this space would be just the infimum of all possible representations. All possible representations. There are always infinite many representations, unless it's maybe, well, even if it's zero, if it's zero, you can't, but well, even zero has many representations, infinite many representations, and you choose, you take the infimum of this. Okay, so that's the norm of this space, and turns out that this space, BSPUT, with this norm, is a Banach space. It's not difficult to prove this. And there is some kind of a Sobolev embedding theorem for this that's really elementary in this setting. Actually, this guy belongs to, is injected on LP. Actually, you can put a plus here, so P plus epsilon if you wanted to. And this inclusion is compact. Okay, so it's really, this is dense here, and the inclusion is compact. So it's really a nice space. And of course, if P is equal to Q, then you say that this is a Sobolev space. Okay. Sobolev. So those are the spaces where you can use in all that cases for all observables in this setting. In all that cases that you see before, you have like with the proper assumptions on topological assumptions, you have exponential decalculations, you have central limit theorem, you have everything, okay? This includes certainly unbounded observables, that very complicated unbounded observables, okay? And in particular cases like in the interval, in the square, if you choose this kind of Alford's regular metric partitions in the manifolds or polyhedron, you got exactly the same classical Besov spaces. Okay, so that's really, it's not like a fake dyadic Besov space, it's the real Besov space, the real Sobolev space that you see in the literature. Okay, I have like 7 minutes, I guess. Yes, okay. So what I'm going to do, I don't have too much time to explain how I prove that the transfer operator is quasi compact in this setting. So to give you even an idea, But what I like about these spaces is that the definition is elementary. You don't need very complex tools to define this space, improve nice properties of the space. And another thing that I like very much is the ability to define this space in very different ways. So there are very different alternative definitions for the same space. One of them that I like a lot is using higher wavelets or unbalanced higher wavelets. So this is something that was, as far as I know, introduced by Maria Girardi. And I don't know how to pronounce the name of this guy, Howdens. This is 1997. It's a very nice paper. I really like this paper. And I discovered this morning that Maria Girardi works in Pisa, right? And is CNR of Pisa. I think it's 2 kilometers from here. I don't know her personally, but I really appreciate this paper. It's really nice. So I'm not going to explain all the constructions of unbalanced high wavelets for a general sequence of partitions, because it would take like probably an hour to explain details. But let me explain a situation that's actually much simpler. That's the binary situation, binary tree. The paper is much more general, and I'm much more interested than this case. So, so what you have is the following. Suppose now that every element of the partition Q, of the partition of level N, has exactly 2 children. Okay, so Q1 and Q2 in the next level. Okay. So in this situation, what you can do is define a function in this guy that's constant here, something like this, right? The graph is like this. And this function, I'm going to call this function like phi q. And this function has the following property. The L2 norm of this with respect to the reference measure is 1. And when you make the product of this function with any constant function, so what I mean, this integral is 0. Okay. So there are just 2 choices: this function or maybe minus this function. Okay. So this is our my higher wavelets. They're unbalanced because the height here and the height here can be different because the measure of this set and this set may be different. Okay. But this is the high wavelet. And turns out that Girardi and Schwelden, hope I'm pronouncing right, they prove it that if you pick the constant function on the phase space and make the union of all these wavelets, this is a inconditional basis for beta bigger than 1. Okay, is using a nice martingale argument. It's a probabilistic argument, as I remember of this. Okay, okay, so it's very nice function because set basis for L2, for instance, inconditional. That means that I suppose you can write to whatever order you doesn't matter. Okay. Okay. So okay. So what is nice about this base is the following. There is a fast wavelet transform for this. You can see the paper that's similar to higher wavelets fast wavelet transport. So this is practical. You can actually calculate the representation in these bases quite fast. Okay. I didn't try myself, but you can do it. Okay. And actually, if you pick some function, arbitrary function phi in these spaces, then you can represent this as a sum of these guys. And what is a little different from the atomic deposition that I told you before is that you have a explicit formula for the coefficients, right? Because this is basically Hilbert basis. So this is just the integral of psi times qk dm. So that's the formula. Okay, that's not an efficient way to calculate this, but that's the formula for this guy. Okay, so turns out that you can define the Besov space using these hard bases. Okay, so what you can do is the following. Suppose you have this representation for psi. So this guy belongs to the Besov space if and only if, exactly the same Besov space, if and only if this norm is finite. So let's call it NER of psi. So this is just basically the sum of all n, the sum of all elements in the partition. You pick the measure of Q to the power 1 minus SP minus P over 2. Pick this coefficients CQ to the power P, Q of P. Hope I'm doing some things fast, but if this number is finite, then it belongs to the Besov space. So that's a very explicit calculation. It's not like before, like an infimum of alt representation. This is a very explicit representation. And if this is finite, that belongs to this Besov space. Okay. In particular, this gives you like a Hilbert structure in the case of a P and Q equal to 2. For instance, you can define an infinite product in this using this formula. Okay. Okay, I have now 30 seconds. No, I don't have any more time. But let me maybe can have 1 minute, just 1 minute. So let me finish to give another alternative definition that is not in terms of basis, but in terms of oscillations. So this is kind of similar to maybe Kähler space, definition of Kähler space. So I can define the oscillation of this function in this element of the partition. I just compare this function with all possible constant functions on Q, okay? And I try to minimize this, like the infimum of all. So I'm just compare the function f with constant functions on Q, okay? So that's the minimal distance between, there's 1 over here. So you can define the oscillation of the function. You compare over all possible elements in the partition. And then you make the following calculation. The power Q, P, okay, this. So this is another norm. And when this is finite, the function belongs to the Besov space. All these 3 norms are equivalent, okay? And well, there are many other things you can do. For instance, instead of using atoms that are so boring like this, you can use atoms that are like holder inside. And surprisingly, you get the same space. Okay, so this is more similar with standard pairs, standard families in Chernoff and Gopiak, especially in the case P and Q equal to 1. So you write the function has a linear combination of a piecewise holder functions and calculate the norm in some way. So that's very nice because there are many ways to understand the same space. Okay, I don't have any more time, so thank you very much for your attention.
Are there more questions for Daniel?
Yes.
Yes, Roberto.
Yeah, a conditional result, right? Well, the condition depends on the structure of the branches, right? But what you can prove that in particular situations like piecewise expanding maps on a manifold, you can prove that this is a genetic condition. Okay, so you don't have genericity results in this setting because I don't know what topology I'm going to use in this space of expanding maps in this exotic phase space. Yes, in many systems are checkable. In all that lists that I showed you, is checkable. So you can check this in all these examples. There is a paper with the theory. There's a paper with examples. There are the third pages of examples. Yeah.
So it's okay.
Okay. Yeah.
I have a different question. I was trying to understand better the dependence on the parameters of the BS space.
Yes.
The norm of the characteristic function of an interval would be.
So these atoms are called atoms because the norm is 1. So the norm of these atoms are 1. That's why they call it these functions has norm exactly 1, if you wish. So you're making combinations of fractions of atoms and calculate the norm of the function in that way using the combination. I don't know if I answer your question.
Can I ask?
Yes, yes.
So for all of them, there's a uniform bound independent on how big the interval is for the characteristic function for all options of SPQ.
So if you pick a characteristic function of an interval in this partition, if the interval is very small, the norm is extremely small. So it goes to 0. Because this...
Oh, but more than bounded then?
Yes.
More than uniformly bounded?
Yes, that decrease to 0 exponentially fast with the element of... We need to pick the element of the partition, right? If you pick something that is not the element of partition, then it's more complicated. I don't know.
But there is a choice of parameters here where the norm of the characteristic function will be
1
bounded away from 0 for all small intervals.
So this would happen if S is equal to 1 over P. So in this case, you cannot consider, you don't have...
Oh, but you don't allow that.
Yes?
You don't allow S equal to 1
No,
over P.
you don't have quasi-compactness if you have this. So this is a very special situation when S is equal to 1 over P is called critical line in the Besov theory. And those are very special maps, okay? So they're like, so for instance, the multipliers of this Besov space, the maps that define bounded operators by multiplication in this Besov space belongs to the critical line. So there are functions in this critical line. So if the potential usually belongs to the critical line, but the observables where you have quasi-compactness, the calculation is not.
Thank you.
Yes.
Okay, I have a question which is not very well posed, but basically you always present the general setting with Banach spaces.
Yes.
But in some cases, I guess it could be, you could find nice Hilbert spaces. Is there like a general morality that you would really lose something by trying to consider always Hilbert spaces, or is there a hope to obtain similar consequences using only always Hilbert spaces?
Usually you get these things quasi-compactness, especially in the case that's non-Markovian, when P is equal close to 1. Okay. So I just have, as far as I know, you just have the Hilbert structure when P in Q is equal to 2. So I don't know. I don't know how to find a Hilbert space with a similar. There is no good space. I see. But for Markovian maps, you can pick Hilbert space. It's fine. Yes, it's much nicer. Yes. 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 Yes, you're right.
More questions? All right. If not, we can thank Daniel again.
Thank you very much.